The best way to improve your expertise in data science is to work on a lot of data science projects. And understanding that, we have brought up this course where we'll be going through a lot of data science projects that are much needed for you in the year 2021.
Before we get started, I want to introduce you to Great Learning Academy, a free learning initiative by Great Learning where you can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains such as data science, machine learning, artificial intelligence, programming, cloud computing, digital marketing, DevOps, management, and many more absolutely free. Award-winning academicians and leading industry experts design these courses. You can also get a free certificate of completion when you enroll and complete these free courses. You also get access to the presentations, code, notebooks, datasets, and quiz. We have courses in English and Hindi to give you the best learning experience in the language you're comfortable with. Check out the description of this video to access the relevant course on Great Learning Academy. So what are you waiting for? Register now and start your learning journey today. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.
So let's go through our agenda. So we'll start off with this amazing football dataset and we'll be doing a thorough exploratory data analysis on this football dataset. Then we'll analyze some of our superhero characters, and these superhero characters would be from the Marvel universe and the DC universe. Then going ahead, we'll analyze one of our favorite TV show, which is Game of Thrones. So we would have this Game of Thrones dataset and we'll be doing a thorough analysis of this dataset. Going ahead, since stats is a very basic and a very fundamental unit of data science, we'll be doing a comprehensive project on statistics as well. Following which, we'll be doing an end-to-end project with the help of logistic regression algorithm. Then, we'll also build a classification algorithm with the help of naive Bayes. And finally, we will be ending this entire session by building a clustering project.
So here, we have the FIFA 20 dataset and we'll be performing exploratory data analysis on top of this dataset. And now we'd have to import all of the required libraries. So we are importing pandas for data manipulation, obviously. Then we have matplotlib and seaborn. So matplotlib is a library which is used for data visualization. Seaborn is also a library which is used for data visualization. So seaborn you can consider as it's an extension of matplotlib, extension in the sense that seaborn is built on top of matplotlib. So these are the three libraries which I would need, and what I'll do is I'll actually restart the kernel so that you're not able to see the output initially. So for you it will be much more easier to understand. Now I'll hit on run and let's wait for these libraries to load. Alright, so we have loaded the required libraries. Then going ahead, we have this file called as players20.csv. So this is a file which I have already loaded in Jupyter Notebook. And to read a CSV file, we would need this method called as read_csv, and this method read_csv is a part of the pandas library. So here, since I have loaded pandas, so I'll write down pd.read_csv, and inside this I will give in the name of the file, which is players20.csv, and I will go ahead and store it in this object called as FIFA, and I'll just hit on run. Now if I would want to have a glance at the first 5 records which are there, so I need to use the head method. So by default, this head method gives you the first 5 records which are there in this data frame. So FIFA.head, and here you would see that you have all of these different columns. So you have the FIFA ID, you have the player URL. So if you'd, so this is a column which just gives you the home page or the description of this player over here. Then you have the short name of this player. So here you have El Messi, obviously Messi, long name is Lionel Messi. You have Cristiano Ronaldo and you have Cristiano Ronaldo's long name. You have Neymar, you have Oblak, you have Eden Hazard. And here this column obviously tells you the age of this person. Here you have the date of birth, then you have the height in centimeters of this player and the weight in kilograms of this player. Then you have the nationality. So Messi is obviously from Argentina, Ronaldo we all know is from Portugal, Neymar is from Brazil, Eden Hazard is from Belgium, and these are the clubs for which these folks play. Cristiano Ronaldo, he plays for Juventus, Messi plays for Barcelona, Neymar plays for PSG, Eden Hazard plays for Real Madrid. Then you've got all of these different stats over here. So for now, we'll just leave out those stats. So let's actually see how many columns are present in this particular data frame right now. So what we'll do is, I will start a for loop and I would want to know all of the columns which are present. So what I'll write down is for call in FIFA.columns, and I will print out each of the column which is present in this entire data frame. So for call in FIFA.column, so what will happen is it will iterate from the first column. So it will start from this first column and it will go to the last column over here, and we are printing all of the columns which are present over here. So for call in FIFA.columns, print of call, when I hit on run, you would see that these are all of the columns which are present. You have FIFA ID, player URL, short name, long name, age, date of birth, height in centimeters, weight in kg, and so on. So you have a lot of columns over here. Now I'd want to know how many records are there and how many columns are actually present in this data frame. So for that purpose, I will use this shape method. I'll write down FIFA.shape and I will hit on run. And you would see that there are 18,278 records and 104 columns. So this is actually a huge data set. I mean, for performing a simple case study. So here 18,278 records would mean that you have a list of 18,278 players in this entire data frame, and 104 columns are just the different features with all of these different players. So we've looked at the shape, and there is this column called as nationality in our data frame. So here, if you go up, you would see that there's this nationality column, and I would want to see how many players belong to which particular country over here. So since nationality is a categorical column, and if I'd want to understand more about a categorical column, I can use the value counts method. The value counts method gives me a frequency count of the different categories which are present. So what I'll do over here is, first I'll give in the name of the data frame, which is FIFA. Then I'll, inside the parenthesis, I'll give in the name of the column, which is nationality. Then I'll use the dot operator and use the value counts method. And when I run this, this is what I get. So you see that in this particular data frame, most of the players are from England. So you have 1,667 players from England. Then you have 1,216 players from Germany, and you have 1,035 players from Spain. Then you have 984 players from France, then followed by 886 players in Argentina. So this basically tells you that in this data set, you have a lot of players from England, and that could also be a reason because you have you have more number of clubs participating in the English Premier League. So you also have all of these relegation zones. So you have tier 1 clubs, you have tier 2 clubs, you have tier 3 clubs. So maybe this data frame comprises of all of the players belonging to tier 1, tier 2 as well as tier 3, and that could tell you why why there are more number of players belonging to England. Then if I would, so let's say from this entire result, if I would only want to have a glance at the first 10 records or the top 10 countries where most of the players belong to, what I'll do is I'll write down FIFA nationality dot value counts, and again I'll just give in 0 to 10 inside this, and when I hit on run you would see that so most of the players belong to these 10 countries over here. Again, at the top, you have England, Germany, and Spain. Then let's say instead of top 10, if I would only want to have a glance at the top 5, so over here I'll write down 0:5, and you would see that I have these 5 countries. I have England, Germany, Spain, France, and Argentina. Now, I would want to make a bar plot for these top 5 countries where most of the players come from. So, if I would want to make a bar plot, I would need to use this library called as matplotlib, and we have seen that we have imported the submodule which is pyplot, and we have given it an alias of plt. So here first I need to set the figure size. So as you see, I'm setting the figure size over here, plt dot figure, and inside this fig size is a parameter inside this method, and using this parameter I set the dimensions of the image. And as you see, I set the dimensions to be equal to 8, 5. Now once I set the dimensions, then I go ahead and create the bar plot using plt dot bar. And when I write down plt.bar, you have all of these different parameters over here. So when we are creating a bar plot, the first parameter which we give inside it should be the categorical values. Now, after that, what we do is we give in the numerical entries over here. So what we do is first, if we say categorical entries, these are the categorical values over here. Now, if I only use dot value counts method, that gives me these categorical values along with these numerical values. But what if I only want the categorical values, only the names of the countries? So in that case, what I can do is I can use the keys method. So here, as you see, till here the command is the same, FIFA nationality dot value count 0 to 5. Then I am using the dot keys method over here, and I will hit on run, and you would see that I am able to extract the names of these top 5 countries without the values. And since I need to pass in categories as my first parameter, this code is what I'm passing in as the first parameter over here. Then going ahead, the next value is the same command without the keys method. Then going ahead, I have another parameter called as color, and I set the color to be equal to green. So G is, again, it's just a short form for the green color. So I have first passed in the categorical entries, then I've passed in the numerical entries, then I have passed in the color over here. Then I hit on run. So here you see that this is the bar plot which we have created, and it's pretty evident, isn't it? This is what we saw in the list as well. So most of the players, they are from England. Then you have around 1200 odd players from Germany. Then you have 1000 odd players from Spain. Then you have France and Argentina falling behind. So let me again head to the chat and see if there are any questions or any suggestions. So guys, I want this session to be quite interactive. So if you have any doubts, if you have any queries, please keep them coming. I'll see how many of these questions can I actually take up. Santosh is asking, how do we know to set the size of figure So this is arbitrary. So you can give in any values over here. So let's say instead of 8 comma 5, if I give in 5 comma 5 and hit on run, this is what I get. So you don't have a standard fixed size for the plot which you're creating. So whatever looks good, so that is what you will use over here. Some of you folks are saying that the dataset is not available right now. So we will update the dataset in the code file once the session is done. So you do not have to worry about that. Avinash is asking how to open Jupyter Notebook on Android. Well, personally, I do not know myself. If you can actually run, if you have an app which helps you run Jupyter Notebook on an Android phone, so you can you can, if you have figured out something, you can let us know in the chat. So that would be helpful for everyone. Vinay Jain is asking, is it necessary to store the data in dictionary type? If you're asking about creating a pandas data frame from a dictionary, no, not really. So you can create a data frame from any of the other data structures as well. So Yash is asking, is it always the case that value counts will give the data in the sorted manner? Yes, you're right, Suyash. It will always give you the data in a sorted manner. Anand Suresh Kumar is asking, can we use dot index instead of dot keys? Well, let's see what actually that does. So now here, if I maybe use dot index, let's see what does that give over here. So as you see, it gives the same result. So, maybe we can actually use dot index instead of dot keys. But then again, dot keys, it is more intuitive, isn't it? So this basically comes down to you, whatever you'd want to use, that would be better. So if you have any more questions, please put them up in the chat. Some of you folks are asking if this video will be available once the live session is done. Yes. So let's say even if you're not able to watch the live session right now because of some work, that is fine. You can rewatch the session later on, because all of the live sessions which we do, they will be stored as it is on YouTube. So you can come back whenever you're free and rewatch it. Right, so on that note, I'll again head back to our course. So guys, again, to the folks who have just joined, if you haven't yet subscribed to our channel, please do subscribe and also hit the bell icon, because that would be, that would be very helpful to us, and that is how we'll be able to reach more people. And also, if you haven't yet liked the stream, please go ahead and like the video and also share it with your friends. That would be much more helpful. So there's a watching of 102 and there are only 97 likes. So if you can quickly like the video and increase the number of likes, that would be awesome. Great. So right now we have looked at the nationality column. Now we will go ahead and do some more analysis. So we have the wage in euro column. Now I'll just show you if we can. So now as you see, like, some of the columns wouldn't be listed over here because this is a huge data frame, but we have this column called as wage underscore euro. So this tells me the salary of these players in euros, and I want to see I'd actually want to see over here which player gets, what is the salary of some of these players. So what I'd want to do is, from the entire FIFA data frame, I'd want to extract only two columns. The first column would be the short name of the player, and the second column would be the wage in euro. And this I will go ahead and store in this object called as player salary. Now that I have created this sub data frame from my original data frame, then I would want to have a glance at the first 5 records of this. So here player salary dot head, I will click on run. Here you see that in the first column I have the short name of the player, and in the second column I have the salary of the player. And here, as you see, Lionel Messi, his wage is, you have 65,000 euros. Then you have Ronaldo with 405,000 euros. Neymar is at 290,000 euros. Oblak is 125,000 euros. And Eden Hazard is at 470,000 euros. So I'm not sure if these are the latest salaries which these players get, but according to this particular data frame, it would seem that Eden Hazard and Lionel Messi actually get more salary than Cristiano Ronaldo. And now, what we will do is I'd want to see who is the highest paid football player. So from this data frame, from this sub data frame, what I'd want to do is I would want to sort this with respect to the wage column. So what I'll do is I'll write down player salary dot sort values, and inside this I have this parameter called as by. And what I'm doing is I'm just sorting this data frame with this column called as wage underscore euro, and I'll set ascending is equal to false because I would want that player with the highest salary at the top, and that is how it will proceed. And this again, I'm storing it back in the same object called as player salary, and I'll go ahead and hit on run. Now I will have a glance at the first few records of this. So when I say player salary dot head, so obviously as you see over here, Lionel Messi is the highest paid football player at 565,000 euros. Then you have Eden Hazard at 470,000 euros, Ronaldo at 405,000, Kevin De Bruyne at 370,000. You have Griezmann at 370,000 euros. So quite an interesting analysis, isn't it? So again, we will do the same thing. We will make a bar plot for these top 5 football players with the highest salaries. And since we have these categorical entries over here, we would have to make a bar plot. So you have to understand why we're using a bar plot. So normally whenever we do want to understand the distribution of a categorical entity, that is when we go ahead and make a bar plot. So here what we are doing is first the same thing, we will set the figure size. So Apurva over here is asking me to repeat the bar plot again. So that is what I'm doing right now. So this time we are creating a bar plot for the players with highest salaries. Here as you see, first I am setting the figure size. So I'll write down plt.figure. Inside this I'm setting the figure size using this parameter called as fig size, and I given these dimensions. So the dimensions are 8, 5. 8, 5, 8 is the width, 5 is the height. So I've given the dimensions of the figure. Now after I set the dimensions of the figure, I can just go ahead and create a bar plot. So to create a bar plot, I'd have to write down plt dot bar. Inside this, so in a bar plot, always remember that the first parameter which you given has to be the categorical entries. The second parameter which you given has to be the numerical entries. So here the first parameter, since it has to be capital, it has to be categorical. What I do is I would have to, so we have a categorical column, we have a numerical column. So obviously it is the names of the players which will be passing in over here. So this basically is your x-axis. So on the x-axis, we would need the names of the players. So I'll extract this particular column. So this short name column is from player salary data frame. So I'll write down player salary, and I given the name of the column which is short name, And obviously I'd want only the top 5 records, so I'll give in 0 to 5 inside this. Then I will go ahead and in the next parameter, as you see, I have a wage in euro. So again, since it has to be numerical, this time I'm extracting the wage in euro column, and I'll go ahead and set the color over here. So color, as you see, is equal to red. Then I will go ahead and plot it out. I will hit on run. And as you see, this is the result which we get. So on the x-axis, we have the names of the players, and on the y-axis, we have the salaries. So Lionel Messi obviously is leading the chart. Then you have Eden Hazard, Cristiano Ronaldo, Kevin De Bruyne, and Annie Griezmann. Now let's say if I would want different colors for all of these different bars over here. So that is something which we can also do. Now let's say instead of just keeping this as red, if I would want different colors, so what I'll do is I'll pass in a list of colors over here. So for Lionel Messi, let's say I give in blue color. Then for, let me just keep it small b. So for Lionel Messi, I'm keeping blue color. For Eden Hazard, I'll give green color. Then for Cristiano Ronaldo, maybe I'll give in red color. Then for Kevin De Bruyne, I'll give, let's make it pink. And finally for Griezmann, let's keep it, let's say, orange. And let's hit run. Seems like we have an error over here. The spelling which I've given is incorrect, so let me just keep pink and I'll hit on run, and as you see, this is the result which we get. So we can change the colors which are there in all of these bars as well. Now what I'd want to do is I'd want to do a simple analysis for the players who belong to Germany. So what I'm doing is, so let's say if I from this FIFA data frame, if I set the nationality is equal to Germany and I hit on run, I get a bunch of true and false values. So when you have these bunch of true and false values, what does this actually mean? So if you have a false over here, this means that in that particular record, the nationality of the player is not equal to Germany. And if it is actually equal to true, then it would mean that the nationality of the player is Germany. So what I'd want to do is, from this list, I would want to extract all of those records where the value is actually true. So I will take this command and I will paste it again inside the FIFA data frame, and I will store it in this object called as Germany, and then I'll print it out. So I'll write down Germany.head. And if I would want to have a glance at the first 10 records of it, so Germany.head, inside parenthesis, I'll write down 10 and I will hit on run. And this is the result which we'll get over here. So as you see, this is the list of all of the players whose nationality is Germany. And now what I'd want to know is, I would want to see who is the tallest German player. So Germany.sort values, I will use by, and I would want to sort this with the height in centimeters column, and I will set ascending is equal to false, and I would only want to have a glance at the top 5 records, so I would want the top 5 tallest players of German nationality, and I'll hit on run over here. And as you see, so you have Aaron Seidel right now as the tallest player of German nationality. His height is 199 centimeters. Then you have Michael Esser, whose height is 198. You have Lars Unestal, whose height is 198 again. Then you have Dominic. Then you have Lucas. So these are the players with the, these are the tallest players. Then similarly, let's say if I would want to sort these players, sort these German players according to their weight, I would want to see which player has the maximum weight. So again, this will be similar.
I'd have to write down Germany dot sort values, and I would have to sort it with respect to weight and ascending. I'll set it to be false and I'll hit on run. This time you would see that weight over here. So it's Lucas Voltoviak who has the highest weight of 103 kgs. Then again you have Lars Unstal whose weight is 103 kg. Then you have Ralph Farman. Then again you have Michael Lesser and you have Nicholas Sule. And then I would want to see who is the highest paid German player. So this time I have the wage in euro column and I am sorting it with respect to the wage in euro. Ascending is equal to false and dot head method. Now if I show you these players, let's see what are these names. So Tony Cruz is the highest paid German player and he plays for Real Madrid. So obviously if you're playing for Madrid or Barcelona, you would be paid a lot. Then you have Marc-Andre Stegen and he plays for Barcelona, so he's the second highest player. And then you have Leroy Sané who plays for Manchester City. Then you have LK who plays for Manchester City as well. Then you have Thomas Müller who plays for Bayern Munich. So top 5 players of German nationality who have the maximum wages. Now again what I want to do is I just want to make a simple data frame again. So I just want what I want is I would want 2 columns. The first column should have the name of the player, the short name of the player. The second column needs to have the wage in euros, and I would want to sort this with their salaries. So Germany, from this data frame, I'm selecting only short name and wage, and then I'm sorting this data frame by their salaries, and obviously I'm sorting this in descending order, and I would want to have a glance at the top 5 records. Now if I click on run, you would see that this is what I get. So obviously it is Tony Cruz who has whose salary is 330,000 euros. Then Stegen has 250,000. Then you have Sani at 195, and at 5th place you have Müller at 170,000 euros. Now after this, what I want to do is from the original data frame, I would want to see who has the best rating for his shooting skills. So what I'll do is from the FIFA data frame, I'll extract only 2 columns. The first column is shot name. The second column is shooting. And I'll extract these 2 and I'll store them in this object called as player shooting. I'll hit on run and I'll go ahead and sort it again. Now when I hit on run, you would see that Cristiano Ronaldo has the highest rating for his shooting skills, so he's got a rating of 93. Then you have Lionel Messi, then you have Harry Kane, then you have Sergio Aguero, and you have Quagliarella. So these are the top 5 players with highest shooting skills. Now similarly, I'd want to see which player has the maximum defending skills. So player defending. So this time from the original FIFA data frame, I'll be extracting the short name, the defending column, which would tell me his defending skills, the rating for his defending skills. I have his nationality and I also have the club for which this person plays for. Player defending. And now I would want to sort this by his defending skills. So obviously player defending dot sort values by is equal to defending, and this has to be in descending order. Then I'll hit on run. So you see that you have Chiellini who plays for Juventus, and he's from Italy. He's got the maximum defending skills. Then you have Van Dijk. Van Dijk plays for Liverpool and his nationality is Netherlands.
Then you have Kulipli, then you have Gordon, and you have Hummels over here. So Hummels plays for Dortmund. And then finally, what I'd want to do is I'd want to analyze the list of players who play for Real Madrid. So Madrid is one of the topmost football clubs across the world, and I'd want to see what makes this club so special. I'd want to analyze the some of the features of different players over there, and that would be the final analysis for today. So what we'll do is from the original data frame, which is FIFA, I will set the club value to be equal to Real Madrid. So from the original data frame, we are extracting only those records where the value is equal to Real Madrid, and that I'll go ahead and store in this object called as Real Madrid again. Now I would want to see who is the highest paid player in Real Madrid. So Real Madrid dot sort values, and I would want to sort it with respect to the wage in euro column. And when I hit on run, you would see that Eden Hazard is the highest paid player in Real Madrid currently. Then you have Luka Modric. So Luka Modric is the second highest paid. Then you have Toni Kroos, Sergio Ramos, and Karim Benzema. So Eden Hazard plays for Belgium, Luka Modric plays for Croatia, Toni Kroos plays for Germany, Sergio Ramos plays for Spain, and Benzema plays for France. And now we have looked at who are the highest paid players in Real Madrid. Now let's also see who has the best shooting skills in Real Madrid currently. So Real Madrid dot sort values, and I would have to sort it with respect to the shooting column. Ascending is equal to false because again I'd have to sort it in a descending order. And as you see, Gareth Bale has the best shooting skills currently in Real Madrid. Then you have Jimmy Rodriguez, who is the second best shooter, followed by Eden Hazard. Then you have Karim Benzema. Then you have Luka Jovic. Finally, I'd want to see who are the best defenders in Real Madrid. So Real Madrid dot sort values, by is equal to defending, and I'll hit on run. And here, as you see, so it seems that Sergio Ramos is the best defender in Real Madrid currently. Then you have Casemiro, after that you have Varane, then you have Carvajal, and finally you have Militao. So these are the top 5 defenders currently who are playing for Real Madrid. So on that note, we will start off with the main part today. And also guys, we have a watching of 85 and we have only 67 likes. So we would need as many likes as we have watching. So if you could quickly make that 85, or if you can even get that up to 100 likes, that would be amazing. So quickly go ahead and hit the like button. And on that note, we will start off with today's session. So as I've told you, we'll be working with these two libraries. We will not actually require Seaborn. So Seaborn is also another visualization library, which we will not require today. So I'll just delete it from this command. So we would need pandas. The alias for pandas is PD. We would need pyplot, which is a submodule in matplotlib. And I'm giving this an alias of PLT. Again, let's just wait for these libraries to load. So that is done. What I'll do is I'll actually remove the results from over here so that it will be much more interactive, so that you actually know what is happening over here. Now, let me start off by running this again. And now, if you'd have to load any CSV file, so CSV file is something which has the extension of .csv, and these are normally your Excel files. So if you have a CSV file, this is how you load it. So you write down pd.read_csv, and read_csv is a method in the pandas library, and we have a CSV file called as character stats, which has all of the statistics of all of your Marvel superheroes and DC superheroes. And this I go ahead and store in this object called as Marvel. Now I'll go ahead and have a glance at the first few records of this Marvel data frame. So I need to write down marvel.head, and by default this head method gives you first 5 records which are present.
So as you see, this is our Marvel data frame, and this comprises of all of these columns. So you have the name of the superhero over here. So you have 3D Man, A-Bomb, Ape Sapien, Abencer, Abomination. Then you have the alignment, whether the superhero is good or so. Basically, we are saying if he's a superhero or a supervillain. So that is what the alignment tells you, whether he's good, bad. You also have another category called as neutral. So I guess there are very few neutral characters which are there in this particular data frame. Then you have the intelligence over here. So as you see, 3D Man has an intelligence of 50, A-Bomb has an intelligence of 38, Abencer, Abomination. So all of these superheroes are alphabetically listed. Then you have the strength of the superheroes. Similarly, you have the speed, durability, power, combat, and total. So these are some columns which are present over here. Now, then we will go ahead and see how many records and how many columns are actually present over here. So for that, we have the shape method. So we will write down marvel.shape and I hit on run. And you would see that this has 611 records and 9 columns. So this 611 records tells you that there are 611 superheroes or supervillains present in this particular data frame. Now going ahead, I'd want to see how many of these characters listed in this data frame. So how many of them are good, how many of them are bad, and how many of them are neutral. So that information will be coming from this column called as alignment. So that is what this alignment column tells us. And this is a categorical column. So all of the other columns are numerical. So as you see, numerical columns would basically mean you have numbers. Categorical column, as the name states, you have categories over here. So if you have to do some sort of analysis on the categorical column, if you'd have to check the frequency of the categories, then we have a method called as value counts. And as you see over here, so first I given the name of the data frame, which is Marvel. Then, so we have this parenthesis. Inside the parenthesis, I given the name of the column, which is alignment. Then I use the value counts method and I hit on run. And you would see that, so out of the 611 characters which are present, 432 of them are good, so we'll consider them to be superheroes. 165 of them are bad, so we'll consider them to be villains, and 11 of them are neutral. So this is some interesting information which we have out of this. And this is a data frame which comprises of both your Marvel superheroes as well as your DC superheroes. Raki Gurjar is asking me to repeat. So could you tell me what exactly do I have to repeat? Raki is saying PLT is not defined. Have you given the exact command over here? This is what you'd have to give from matplotlib import pyplot as PLT. If you're given the exact same command, this needs to work. And if you haven't, then maybe there might be some installation issues. So you just have to install matplotlib by going to Anaconda and writing pip install matplotlib. So that should help you out over there, Raki. So now that we have had a look at the different categories which are present over here, what I'd want to do is I would want to extract all of these good characters from this entire data frame. So out of these 611 characters, I'd want to extract all of the good characters. So let me explain this command properly to you folks. So what I'm doing over here is, so first, when I given the name of the data frame, inside this I given the column name. So let me write down alignment over here, and when I set the alignment to be equal to good, what this actually does is this gives me a bunch of true and false values. So wherever the value is true, this would mean that the record over there is equal to good. Wherever we have a false, this would mean that the record over there is bad. So here, as you see, so you have 0, 1, 2, 3, 4. You have these index values over here, and if we go up, so we had true, 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 and false. You had trues for all of these because you have good over here. You have a false for this because you have a bad over here. So this is how we give the condition. Now, out of these true and false values, I would want to extract only those records where the value is true. So what I'll write down is, I'll give in Marvel over here. I'll cut this out and I will paste it inside the Marvel data frame. Now when I hit on run, and if you look at this particular data frame over here, so you would see that I have only extracted the superheroes out of the entire data frame. So this is something interesting which we've done. Now, so again, good.head over here will give me only, so what I'm doing is the same command over here, I'm storing it in a new object called as good. Then I go ahead and have a glance at the first 5 records. So again here, you'd have to understand that this is alphabetical. So when we say alphabetical, again, if you have any superhero who has a number, who has his name starting with a number, so that's why you have 3D man at the top. Now, I'd want to see which of these superheroes has the maximum speed. So, speed over here is a numerical column, and if I'd have to sort my data frame with respect to a numerical column, I have this method called as sort values. So I will write down good dot sort values, and I would want to sort this data frame with the help of the speed column, and I will set ascending is equal to false because I'd want this data frame such that that particular superhero whose speed is the maximum, his record is at the top place and it goes in a descending order. And I'd want to have, so let's actually remove head over here. Let's have a look at the complete list of this data set. So here, as you see, Flash 3. So Flash obviously has the maximum speed. Then you have Jack of Hearts with a speed of 100. You have Impulse with a speed of 100. You have Stardust with a speed of 100. You have Quicksilver with a speed of 100. So seems like there are a lot of superheroes who have a speed of 100. Let's actually see how many of these superheroes have exactly a speed of 100. So what I'll do is I'll again insert a cell above this. Now from this data frame, from the sub data frame good, I have this speed column and I want the speed to be equal to 100. And this I will store in an object called as max speed good. I'll actually have to again store this in a data frame. So let me cut this out over here, paste it over here. Now I will go ahead and insert a cell above this, and I'll have max speed good. So it seems like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So it seems like we have 12 superheroes who have a speed of 100. So this is quite interesting over here, isn't it? So if you so again, this is, you'd have to keep in mind that this is with respect to alphabetical. So you have Black Bolt, Flash 1, 2, 3 and 4. So again, so you have different versions of Flash over here on the basis of the comic book. So you have, again, Flash is obviously the fastest superhero. His speed is 100. Then you have Crypto, Nova, Quicksilver, Stardust, and obviously Superman. So Superman can fly. So obviously we are assuming that if Flash is the fastest person on land, then Superman must be the fastest person in air. So that could be a reason why Flash and Superman have the same speed level over here. So this is quite an interesting analysis. Now, let's say if I'd similarly, let's say if I'd want to find out all of those superheroes whose speed is the lowest. So you have, as you see over here, there are a lot of superheroes whose speed is only 1. So what I'll do is I'll change this to equal to 1, and I will change this to min speed. So min speed good. So here, wherever the speed value in this good data frame is equal to 1, I'll be extracting all of those records, and I'll store that in min speed good. Then again, I will have min speed good over here. So here, as you see, all of these superheroes do not really seem to be, that strong. So all of these values are quite low over here. Their intelligence, strength, speed, durability, and power, they are extremely low. So White Queen, Wizkid, Wandra, so all of these, I'm pretty sure that you wouldn't even have heard of all of these superheroes. So these must be just random characters in the Marvel DC universe who have extremely low stats with respect to this. So similarly, what I'd want to do is I'd want to see who is the most powerful superhero. So we have a tab called as power. So again, good dot sort values. So I'll delete min speed good, and over here I'll also delete this. So now from this data frame good, I'd want to this time, so initially we had sorted this with respect to speed. Now I'd want to sort this with respect to power. So as you see, good dot sort value, still here it's the same. It says that when it comes to buy, I am sorting this data frame with the help of this power column, and I'll set ascending is equal to false because I don't want the superhero who has the maximum power to be at the top. So again, let's actually have a glance at only the first 5 records. So here, as you see, we've got these records over here. So you have Zatanna, Thor, Beyonder, Beta Ray Bill, who have a power of 100. So that's quite interesting. And I'm personally a big fan of Thor. So if you've seen Avengers Endgame, then you have fat Thor in Avengers Endgame. So even though he was fat, he was extremely strong. So I personally love Thor's character in Marvel's Endgame. What do you guys think about that? So now, similarly, what I'd want to do is I'd want to extract all of those superheroes who have a power of 100. So here, good. Again, I need to give in the name of the column, which is power, and I will set the power value to be equal to 100. Then again, I'd have to extract this. So again, this will become good. I'll cut this out. I'll paste this in the good data frame, and I will store in, let's say, I'd have to store this in good. Let's just say actually good max powerful. I'm just giving random name over here. I'll insert another cell over here. So let me just good max powerful, and when I hit on run, so seems like we have a lot of superheroes. So as you see over here, we have a lot of superheroes. Let's actually see. Let's actually get the count of this. So again, I'll insert a cell about this over here. Let me see the shape of this. So Control C, Control V dot shape, and when I hit on run, so you would see we have 33 superheroes who have a power of 100, and that is amazing, isn't it? So you have all of these superheroes, and this is right now listed in alphabetical order. So let's see how many of these superheroes are actually famous, are actually there in the Marvel or DC universe, who are quite famous. You've got Doctor Strange over here, who obviously is extremely powerful. And then, seems like we also have Goku. So if some of you watch anime, so seems like, I don't know if Goku comes under why Goku has been listed over here, but seems like we also have Goku over here. Then obviously we have Iron Man with a power of 100. Then we have Martian Manhunter, we have Marvel Girl, we have Nova, Silver Surfer. Something interesting over here. So if you see, we do not have Superman. So this is quite interesting, isn't it? So let's actually go up and see what is Superman's power. So this is something we had done above. Where was that? Sort values, speed. Okay, seems like we've lost that. So anyhow, so as we were looking over here, so seems like Superman does not have a power of 100, so that is something interesting to find out over here. So I'll quickly head on to the chat and see if there are any more questions. Diya Banerjee Das is asking, is the value count method case sensitive? Yes. Python in general is case sensitive, so you'd have to keep in mind that anything you're typing out in Python, it has to be case sensitive. Jeevan Sharma is asking if it has any missing value, what do we do? So right now it does not have any missing value, so we'll not really look into that. Mohit Joshi in 33.9, what is 9? 9 is the number of columns. So in 33.9, 33 is the number of records and 9 is the number of columns. So folks, put in your questions over here. I'll keep taking up your questions in between. Mohit Joshi is asking false means bad or neutral. So what we were doing is the condition which we gave was something like this. Where was the condition? Marvel.shape. Right. So here what we are doing is wherever, so this is the condition which you give. So if this condition is met, if the alignment is equal to good, then you'll get a true value, else you will get a false value. That is how it works. Vinita is asking if out of those 611 heroes, if we'd want to check out anyone specific, so you'd have to give in the exact name of him. So let's say if I want to check, let's see, who do we have over here? Let's actually check Thor. So if I want to check only the record of Thor from this entire data frame, what I'll do here is I'll write down, I'll give in the name of the data frame, which is good. Then I have a column called as name, and what is the name of the superhero? It is Thor. And this is what I'll do. This is the condition, and again I will keep it in the good data frame. I'll put it inside this and I'll hit on run. So as you see over here, I have extracted only this particular record where the name is Thor. So this is how we can analyze some specific records from the entire data frame which we have. So we have done analysis till till the power of all of these superheroes. Now what I want to do is, so till now what we've done is data manipulation. Let's actually do a bit of data visualization. So when it comes to data visualization, again we will be needing matplotlib, and matplotlib again has a submodule called as pyplot, for which we have given this alias of plt. Now I will insert a cell above this, and what I'd want is I would want to make a simple bar plot for the top 5 superheroes with maximum power. So here we have this particular over here max power. I'll actually get this again. So here we have this particular record. So as you see, we have the top 5 superheroes with maximum power. Now what I'd want to do is, if I'd want to make a bar plot of this list, so not actually power, so you see this total column over here. So I'd want to look at the top 5 list of top 5 list of those who have the maximum total value, right? So here as you see, Martian Manhunter seems to be he seems to be best when it compares to everything, right? So Martian Manhunter, only when it comes to speed and combat, it is less than 100. For in all other aspects, he's got an absolute 100 over here. And we were talking about Superman. So Superman, it seems that he does not have a power of 100. He only has a power of 94. So this is quite interesting. So seems like Thor is much more powerful than Superman, which is quite an interesting take, isn't it? Then you have Stardust, Thor, and Supergirl over here, and these are the total values. Now, so these total values basically indicate the most powerful superheroes in the DC. And when I say powerful, that would mean with respect to all aspects, with respect to intelligence, strength, speed, total power, and combat. So obviously if you add all of these, this is what you will get over here. So now what I'm doing is I'd want to have a look or make a simple bar plot for all of these top 5 superheroes. across DC and Marvel franchises. And to make a bar plot, first we would need to set the dimensions, and I am using plt.figure, and inside this I have a parameter called as fig size, and I set the figure size to be equal to 8,5. So these are just the dimensions of the image which I'd want to create. Going ahead, if I'd want to create a bar plot, I would have to use plt.bar, and in plt.bar you have these three different parameters over here. The first parameter which I give, normally when you're creating a bar plot, the first parameter needs to be a categorical entry, and that is what we are doing over here. So you have good max power, so this is from good max power. First, on the x-axis, I would want to list out the names of the superheroes, and on the y-axis, I would want to list out the total values. So first, I will extract all of the names over here. So as you see, good max power name. So obviously 0 to 5, because I only want the top 5 superheroes with the most total value. This is what I'm giving as the first parameter. Then in the second parameter, I will take in the total value. So this time from the good max power data frame, I am extracting the total column. Again 0 to 5, because I do want the top 5 columns. And I'll give a color to this bar plot, which is basically green. So if I give in color is equal to G, that would basically mean that the bar plot which I've created is of green color. Then plt.show, and this is the result which you get. So as you see, these bars are, there's not much of a difference, but these are slightly decreasing. So Martian Manhunter, Superman, Stardust, Thor, and Supergirl. So this is a bit of visualization which we have done. Siddharth Chandal is asking, can you please give a short intro on what does Panda do? So I've done this in the start of the session. So if you have joined in late, maybe once the session is done, you can go back and quickly check it out. What is Pandas, and how are we doing all of this? And guys, for those folks who have just joined in, I'd request you to subscribe to our channel and hit the bell icon. So we'll be doing a lot of these sessions on a regular basis, and also we'll be uploading a lot of tutorials. So if you're interested in data science, data analytics, machine learning, AI, or maybe other domains such as cloud computing, DevOps, so we have tutorials on all of these different domains, and we keep uploading them on a regular basis. So please do subscribe to our channel, and please do hit the bell icon, so it will give you regular notifications, and also it will encourage us to come up with more such live sessions. Siddharth is asking, if the graph is 5 cross 5, why are we specifying 8,5? These are the dimensions, Siddharth. So this is not actually 5 cross 5. Let's say if I change this to maybe 10 cross 5, you will see that the dimension will change. So as you see, 10 over here is for the, what do you call this? So this is the width, and 5 over here is the height. Now let's say if I change this to maybe 10 and 2, let's see what will this look like. So as you see over here, so again we have changed the figure size over here. If you just want it to be maybe 5,5, keep it 5,5 over here. So again, so as you see, 5,5 doesn't really look that great, so I've given 8,5 over here so that these bars are more spaced out. So I hope that answers your question, Siddharth. Amar is asking, can we get the code in the dataset? So someone from my team would have posted the link for the code in the dataset, so you will be able to get that over there. So guys, also quickly, those folks who haven't yet subscribed to our channel, quickly subscribe, and also if you haven't yet clicked the like button, please do like it, as this will this is how you can show your appreciation to us. This is how you can show your love towards us if you like the session. So please do like the session. And we have done this basic analysis for all of the superheroes. Now let's actually do the same sort of analysis for villains as well. So this time from our original data frame, which was Marvel, I am extracting all of the records where alignment is bad. So as you see over here, Marvel alignment is equal to bad, and I'm storing this in this object called as bad, and I click on run over here. Then I have a look at the top 5 records. So you have all of these villains over here, or super villains: Ammo, Amazo, Airwalker, Abraxas, Abomination. Now I'd want to see who has the maximum speed among these super villains. So again, it will be bad dot sort values, and this time by it will be speed ascending is equal to false. So similar stuff what we've done, and as you see over here, so you see that a lot of these super villains also have a speed of 100. So you have Zoom, Airwalker, you have Amazo, you also have General Zod over here. So then you have Superboy Prime. So all of these supervillains have a speed of 100, which is quite interesting. Then similarly, I want to see who is the most intelligent among these supervillains. So this time I will sort it by intelligence. I'll click run. And as you see over here, you have Mr. I'm not sure how do you spell this, but this, so Mr. MXYZPTLK seems to have an intelligence of 113, which is amazing. Then you have Lex Luthor, the villain in the Superman series. Then you have Leader, you have Brainiac, and then you have Doctor Doom with an intelligence of 100. So this is something interesting over here. Then I'd want to see who is the most, badass of all of these supervillains. So again, I would want to look at the total column over here. So bad dot sort values, by is equal to total, and ascending is equal to false. So it seems that Superboy Prime seems to be the most powerful among all of these supervillains. Then you have General Zod, then you have Amazo, then you have Dormammu. Dormammu again was the villain in Doctor Strange comic series. So if you've seen the movie Doctor Strange, then you would know about Dormammu from that movie. So it was also amazing how in the end, Doctor Strange was able to put Dormammu in a time hole. So if you've seen Doctor Strange, you will find that quite interesting. So you will see that, how Doctor Strange, who is equally intelligent as Dormammu, who is able to outwit Dormammu over here. Then going ahead, what I'd want to do is, similarly, I would want to make a bar plot out of this. So I would want to make a bar plot for these top 5 supervillains over here. So again, plt.figure, fig size, dimensions 8,5. So if you want me to change this, I will maybe change this to, I don't know, let's keep it 10,5. I don't know, 10,5 seems fine. plt.bar. So someone in the chat has asked how to give different colors in the bar. So I'll show you how it's done. So plt.bar, here the first parameter will be the name of the supervillain over here. So that is why I'm giving the name column. Again, I would need only the top 5 records. Next is the total column. Then over here inside color, I'll give in a list of colors. Since I have 5 bars, so I have 5 superheroes for which, 5 supervillains for which I'd have to create this bar plot. So inside this parenthesis, I'll give in 5 colors. Let's say the first color is red. Next color I'll give in green. Then I'll give in blue. Then I'll go ahead and give in, let's say, orange. And then final color, let's say I'll give in pink over here. And I have plt.show. Why do we have an error over here? Bad max bar. Okay, let me also run this first. Now let me run this, and as you see, I have different colors for each of these different bars over here. So again, this will come sequentially. So the first bar has the red color, second bar has the green color, similarly followed by blue, orange, and pink. So I hope that answers your question, Venkata. So this was about the supervillains. Now, what I'd want to do is I'd want to make a distribution of speed for all of the superheroes. So I'd want to see what is the range of the speed for all of the superheroes. So since speed is a numerical column, what I'm doing over here is, again, setting the dimensions over here, plt.figure, figure size is 5 and 7. Then I will go ahead and use plt.hist. So plt.hist, which I'll be using to make a histogram, and here you'd have to understand the difference between a histogram and a bar plot. A bar plot is used to visualize something with respect to categorical columns, and a histogram is used to visualize something with respect to numerical columns. And as you see over here, since we have names over here, since we have categories, that is why we've made a bar plot. Now on the other hand, if I just want a distribution of speed, so speed is only a numerical column, that is why I'm making a histogram. So I'll write down plt.hist. So from all of the superheroes, I am only making a histogram for all the superheroes. Then I'll set the title for this as distribution of speed. I'll set the X label to be equal to speed, and then I'll just print it out. So this is something interesting over here. Let me increase the width. Let me make it 10 actually. That would be interesting. Let me decrease the height. 10,5 would be better, I believe. Right. So as you see over here, most of those superheroes, their speed would be somewhere between, so you have 140 superheroes whose speed would be somewhere between 0 to 10. And there are very, very few superheroes. There would be around 20 odd superheroes whose speed is between 90 and 100. You have two peaks over here. So there are 140 superheroes for a speed of 0 to 10. And there are around 85, or you can say somewhere between 85 superheroes whose speed is between 20 and 30. So this is how the speed of superheroes varies. Then similarly, if I'd want to have a look at the combat for all of these superheroes, again I'd have to do the same thing. It'll be plt.figure. I'll set the figure size. I will make it 10,5 actually, because it'll be better to visualize. plt.hist. So now this is actually the combat for super villains, because I'm using bad over here. So let me change the comment over here. Let me change this to be equal to super villains, and title as distribution of combat, and here X label as combat. And here you see, again, there are also we have very few superheroes, very few supervillains in general. So out of those very few supervillains, there would be around maybe at max 10 supervillains whose combat value lies somewhere between 90 and 100. And there are around 40 supervillains whose combat is between 0 to 10. And again, you have a peak over here. So there are around 30 odd villains whose combat rating is between 50 and 60. So this was all about the exploratory data analysis for the Marvel and DC superheroes. Let me again come back to the chat and see if there are any more questions. Neeru Gupta is asking if there's a Blender tutorial. So right now, I believe we do not have a tutorial on Blender. So again, we'll keep that in mind, and we will come up with a session on that soon. So also, if you have any requests on what we are supposed to take up, please put them up in the chat. So let's say if you like this session and if you'd want to learn more, then let us know in the suggestions. So, we can, if we look at those suggestions, and if it is something our team can take it up, we'll definitely have a live session or a video on it coming up. So this will be it from my side. And if there are any final thoughts or any final questions from you guys, please go ahead and put them up. I'll just wait for a couple of minutes so that you can put in your final words, final suggestions or questions. Viplav is asking, will this class remain here or not? Yes, this class will remain here. So whatever live sessions we take, those are available on our YouTube channel. Pinkita is asking us to make a video on scopes. Sure, we will take that up. Mohit is asking, what if I need only some selected columns as an output, not all columns? Sure, I will show how to do that. So let's say from the original data frame, which is Marvel. Now I'll write down Marvel. From the Marvel data frame, if I'd want only the name column and the total column, so this is how I'll do. First, I'll give in this column, the name of this column, then I'll give in the name of this column. Then maybe I'll store it in a new object and I'll call it as Marvel total. I'd have to give in 2 braces over here. Let me cut this out. Let me paste it inside this. Now let me print out the head of this. So it will be Marvel total dot head. And as you see over here, I have extracted only 2 columns from the entire data frame. So you just need to give in the name of the data frame and inside the parenthesis, so you need to give in 2 braces over here, and inside those 2 braces, you need to give in the columns that you'd want to extract. Santosh Kumar is asking, what were these superheroes doing in the pandemic? Interesting question, Santosh. So maybe I guess they were following the lockdown protocols. Who knows? So I guess even superheroes were staying at their homes. You don't really know. So I guess on that note, we can end this session. Thank you very much for attending, and hope to meet you in future live sessions. And again, on that final note, if you haven't yet subscribed, please do subscribe to our channel. Now, let me quickly jump onto this. So we would require with these 2 libraries, which we have learnt about. So we have learnt about pandas, we have learnt about NumPy. Now I have quickly loaded these 2 libraries. Now I have this data frame called as battles. So this is a CSV file which comprises of different battles which have happened in the Game of Thrones series. So to load this file, I'll just write down pd.read_csv. So this read_csv method helps us to load a CSV file. So this is how I'm loading this file, and I am storing it in this object called as battle. I have successfully stored it. Now I'll have a glance at the first 5 records which are present in this battles data frame. So we have our, this is the first of 2 data sets of the Game of Thrones. So here in this data frame, we have all of these columns over here. So this name which you see is the name of the battle. So we have around maybe 40 odd different battles which have occurred through the 7 books. So you have Battle of the Golden Tooth, you have Battle at the Mama's Ford, you have Battle of River Run, you have Battle of the Green Fork, and so on. This column tells us in which year the battle occurred in. So Game of Thrones was mostly based throughout the 298, 299 and 300 AC years. Then you have the this column which would tell you who is the attacker king. So here for this battle, which is Battle of Golden Tooth, the attacker king was Joffrey and Tommen Baratheon, and the defender king was Robb Stark. So here attacker 1 basically tells you who is the primary attacker. So primary attackers are Lannisters over here. I mean, we already know that the Lannisters have started most of these wars, so this is not really not really new information. Then we have this major death column. This major death column tells us if any major death has occurred in this war. So let's say if someone such as maybe Jaime Lannister has died or Robb Stark has died. So if there's any major death involved in this battle, then we'll have the value 1. On the other hand, if there's no major death, then we'll have 0. Similarly, we have this major capture column. So if the value is 0, it would mean no major captures have occurred in this battle. Similarly, if we have the value 1, that would mean some major captures, someone really powerful has been captured. Then we have attacker size over here. Attacker size would tell you the number of people who have fought on the attacker side.
Then you have who's the commander who is leading the army of the attacking side. Similarly, you have this column which would tell you who is the commander who is leading the defender side. Then you have the different regions in which all of these battles occurred. So let's say if we take this particular battle, which is Battle of the Golden Tooth. So this battle has occurred in Westerlands. So this is some basic information about our data frame. So before we do ED, it's actually important to understand what is the data about. Now, if I want to know the number of rows and number of columns which are present in this data frame, I'll just have battle.shape, and you would see that we have this value 3825, which would basically mean there are 38 records present in this data frame and 25 columns present in this data frame. Now, some of these columns are not very intuitive. So let's say I have attacker 1 over here. Now instead of attacker 1, I'd want this to be more intuitive. So I'd want to rename this column from attacker 1 to primary attacker. So for that purpose, I have this method called as rename. I'll use this rename method. I'm using this rename method on top of this battle object, and inside this I have this parameter called as columns, which would help me to rename this column. So for this columns, I'll pass in a dictionary. Key would be the column which I'd want to rename. Value is to which particular value would I want to rename this column. So I am renaming this column attacker 1 to primary attacker. And when I set in place is equal to true, this would mean that the change directly happens in the data frame itself. Now once I make that change, I'll just go ahead and have a glance at the change data frame. So you would see that initially the name of the column over here was attacker 1, but after using this particular method, we have changed the name of the column from attacker 1 to primary attacker. Similarly, we have the defender 1 column over here. Defender 1 means who is the primary defender. So here I'll use the same method, which is battle.rename. So rename is the method, and I'm using this method on top of the battle object, and I'll have this parameter columns, and you would see that I'm passing in this key value pair. Key is this particular column, value is to which value I'd want to change this name to. So I am renaming defender 1 to primary defender, and when I set in place is equal to true, the changes automatically are saved in this data frame. Then I'll have a glance at this modified data frame. So you would see that I have changed the name over here. So this was some basic pre-processing for this data frame. Now, if I'd want to know how many times a king has attacked. So I have this attacker king column. So let's say if I'd want to know the number of times Robb Stark has attacked someone, the number of times Joffrey and Tommen Baratheon have attacked someone, then I can use the value counts method, which would give me the frequency of a categorical column. So this is a categorical column, as you see. So all I'll do is I'll have battle, and inside this I'll give in the name of the column, which is attacker king, and when I use the value counts method on top of this column, this will give me the frequency of values. So here it would seem that Joffrey and Tommen Baratheon have attacked 14 times. So it seems like Joffrey and Tommen are mostly the starters of all of these wars which have happened in Game of Thrones. And over here when we see Stannis Baratheon, so Stannis Baratheon has only attacked 5 times. Then similarly we have Robb Stark over here. So Robb Stark has started an attack 10 times. Then we have the Greyjoys. So the Greyjoys have started the attack 7 times. So this is a simple information which you can find out about attacker king. And if I want to know how many battles have occurred in different locations, so we have the location column. Now, let's say if I want to know how many battles have occurred at Golden Tooth, how many battles have occurred at River Run, then I'll just use value counts again for this particular column. And you would see that Winterfell and River Run have the most number of battles. So at Winterfell 3 battles have occurred. Similarly at River Run 3 battles have occurred. But from over here to here you would see that only 1 battle has occurred at these different locations. And we have, let's say, we have Storm's End over here. Storm's End again has only 2 battles which have occurred. So that was understanding about those categorical columns. Now that is done, what we'll do is we'll do some basic visualization to understand this data frame better. So to do visualization, we have already imported the Seaborn and Matplotlib earlier. So these are the 2 important libraries for visualization. I'll go ahead and load these 2 up. Now that these 2 are loaded, I'd want to understand, how many, so over here we had looked at the frequency of attacker king. So now I'd want to know, so here what I'm doing is, let's say if a king has attacked, then I'd want to know what is the size of his army. So that is why I'll have attacker king mapped onto the x-axis, attacker size mapped onto the y-axis, and I am creating this bar plot on top of the battle data frame, obviously. So here this SNS.set, I'm just setting the figure size over here because there are a lot of things which are present in this visualization. So here we have 4 attackers. We have Joffrey and Tommen Baratheon, then we've got Robb Stark, then we've got the Greyjoys, and then we've got Stannis Baratheon. So here, it seems that whenever Stannis Baratheon attacks, he has a huge army size. So if you look at Stannis Baratheon's army size to other Baratheons, or to even Robb Stark, or to even Greyjoy, so if we look at this, so Stannis Baratheon, he would have a size of around 30,000 in general. Similarly, if we look at Greyjoys, maybe sorry for that. So Greyjoys would have the army, the size of their army would be somewhere maybe close to around 1,000 or 2,000, not more than that. Similarly, Joffrey and Tommen Baratheon, their army size would be around close to 10,000. So this is an interesting observation. So it seems that Stannis Baratheon had a huge army along with him when compared to other attackers. Now similarly, if I'd want to know the army size of the defender, so this time what I'm doing is I am mapping the defender king onto the x-axis, and I'm mapping the defender size onto the y-axis. Now when I run this, so these are all of the defenders. So this time we see that whenever, so out of all of these kings, whenever Renly Baratheon was attacked, he had the maximum army size. So maybe in some battle, Renly Baratheon would have been attacked, and in that particular battle, he had an army size of 20,000. Then followed by Joffrey and Tommen Baratheon over here. So it seems that whenever Joffrey and Tommen Baratheon are attacked, their army size is around 8,000 to 9,000. Then we've got Stannis Baratheon. Now compare this to this over here. So whenever Stannis Baratheon is attacking, it seems that he'll have a larger army. But on the contrary, whenever it's Stannis Baratheon who is being attacked, in that particular point, it seems that he'll have a very small army. So this is very interesting, isn't it? So that was about attacker size, and defender size. And now if I want to know what are the different battle types that these attackers have engaged in. So this time I'll be using this method called as count plot, and I am mapping the attacker king column onto the x-axis, and hue. Hue basically determines the color of these bars. So the color of these bars is being determined by the battle type. Now when I hit on run, so you would see that again we have the same attackers who are Joffrey, Tommen Baratheon, Robb Stark. So we've got the Greyjoys, then we've got only Stannis Baratheon. So it would seem that when it comes to Joffrey and Tommen Baratheon, they mostly engage in a pitched battle, and it's they have ambushed someone very few times, right? So Joffrey and Tommen Baratheon, they have been in a pitched battle 6 times, but they have only ambushed someone 3 times. But when you talk about Robb Stark, so it seems that Robb Stark mostly ambushes his enemies or ambushes, against someone else. So Robb Stark has ambushed the opponent 5 times. And then you have the Greyjoys. So it seems that it's only the Greyjoys who have engaged in this raising type of battle. Then you have then you have Stannis Baratheon. So here, if you look at this, you have no orange color bar, which would mean that Stannis Baratheon has never ambushed anyone. So either Stannis Baratheon was part of a pitched battle or he was part of a siege battle. So quite interesting observations over here. Now there is another data set. So till now we were looking at the battles data set. Now we have another data set called as character deaths, which would tell me about the different deaths which have occurred over here. So I have this character death CSV file. I am storing it in this new object called as death, and then I'll have a glance at the first few records. So these are the names of all of the characters who have died in the series. So, and this is in alphabetical order over here. So you have you have Adam Marbrand, who was whose allegiance is Lannister. You've got Adric Humble, who belongs to the Greyjoy clan. Then you have the death year over here. So death year, obviously it has occurred either at the year 298, 299 or 300. Then you have the Book of Death. So in which book has this character died? So when you have 3.0, this would mean that this character has died in the 3rd book. When you have 5.0, this would mean that this character has died in the 5th book. Then you have the death chapter, which would mean, so in the 5th book, Adric Humble has died in the 20th chapter. Similarly, Aegon Frey has died in the 3rd book in the 51st chapter. So interesting observation again. Then you have the gender over here. So if the gender value is 1, that would mean this guy is male, and if the gender value is 0, that would mean this character is female. And then you have nobility, which would tell you if this person is is actually noble or not. Then you basically have all of these names of different books over here. So this is the 1st book, this is the 2nd book, and so on, which will tell you if this person has appeared in this particular book or not. So that is pretty much it about this. Now what we'll do is we will look at the shape of this. So we have 9, 17 and 13, which would mean that there are 917 records which are present in this data frame and 13 columns present. So overall we have 1917 deaths. Now if I want to do a gender comparison with respect to the number of deaths over here, so I will just pass in this gender column and I'll use the value counts method. And here you would see that out of these 917 characters who have died, 760 of them are male characters. So 760 male characters have died, and it's only 157 female characters who have died. Similarly, if I'd want to know how many people who have died belong to nobility and how many of them do not belong to nobility. So this is sort of even. So out of all of the people who have died, 487 are not nobility, and 430 of them do belong to nobility. Then similarly, what I'm going to do is, so this was with respect to the character categorical columns. Now if I want to understand about the death year, which basically means in which year how many number of deaths have occurred, I'll use count plot over here, and inside count plot I am passing in the death year column. So you have this death year. This is the column which I'm passing over here, and when I hit on run,
you would see that. So you have all of these years. So these books basically depict this particular decade or this particular time zone from 297 AC to 300 AC. So it would seem that most number of deaths have occurred in the year 100 and in the year 299. So you have close to 160 deaths. So that's huge, isn't it? So you have close to 160 deaths which have occurred in the year 299 AC. Similarly, in the year 300 AC, you have around 100 deaths occurring. Then in the year 298 AC, you have around 42 deaths occurring. So it seemed that there was a lot of peace in year 297. There were maybe a lot of battles did not occur in that year, or maybe people were just more, more peaceful. So maybe you would have around only 5 to 6 deaths occurring in this year. So interesting plot again over here. So after this, now I'd want to know, out of these characters who have died, to which allegiance do these people belong to? Allegiance is basically to which clan have they, do they fight from? So again, for this, I'm using a count plot. Let me zoom this for you guys so that the text over here is clear. This is too much of zoom, so let me reduce this a bit. So if we look at this, so this is none. So you basically, so basically these are people who have died, but the allegiance is not stated. So it would seem that most of the deaths belong to the Night's Watch. So you have around maybe 110 or 115 deaths from the Night's Watch side. Then you have, then it seems to be some allegiance over here who have around close to 100 deaths. Then you have the Greyjoys. So the Greyjoys seem to have around 50 deaths. Then we have the, let's say, House of Stark. The House of Stark has around maybe 30 odd deaths over here. But if you compare the other houses, so let's say if you talk about House of Baratheon, seems like very few people have died from the House of Baratheon. And similarly, if you look at the House Tyrell or maybe even House Martell, very few deaths have occurred from their side. So all of this is all of this is the exploratory data analysis which I have done with respect to the different columns which are present in this data frame. So this brings us to the end of this session. If you have any doubts, go ahead and put them up. So I'll take a couple of questions more. So for folks who are asking for the data frame and the code file, you can get it on Great Learning Academy. You will find the link for it over here. Sunita is asking where can she find information about different methods. So if you, I mean, we don't have the time to explain all of the, about all of the methods which I've used over here. So if you want to know more, just given the column name in Google, just search for it and you'll directly find it. Tamila India is asking what is the use of figure and fixed size. So figure and fixed size would help us to reshape this. So over here, let's say I have given the size to be equal to 13 and 5, but instead of 13 and 5, if I keep it to be, let's say 13, I'll actually make it 15 and 10. Now when I hit on run, you would see that the size of this image has changed. So you can go ahead and change the figure size with this command over here. Most of you guys had the same question with respect to figure.fixed size. So we have used to just change the dimensions of the figure which we have plotted. Justin is asking us to do a similar soccer analysis using Python. Sure, we'll absolutely do that. So we'll take up a new soccer session. Maybe we'll have FIFA analysis with Python. So that is something which we can definitely do. Okay guys, so I'll take a leave from my side. Thank you very much for attending the session. And before I actually drop off, if you haven't yet checked out Great Learning Academy, please go ahead and do that. You will find the link in the chat. And also you can check out our app. So the link for the app will also be present.
And if you haven't yet subscribed to our channel or hit on the bell icon, please do that, as you'll be notified whenever we are coming up with more such new sessions, and it will also personally encourage us to provide you with more such high quality tutorials on a regular basis.
The word statistics refers to the idea that comes from the statistical way of thinking, which, as I said, opposed to the machine learning way of thinking, tends to be a little more problem first, data next, which means we worry about things like hypothesis and populations and sampling and questions like that. And the descriptive part refers to the fact that it is not doing any inference. It is not predicting anything. It's not prescribing anything. It is simply telling you what is there with respect to certain questions that you might possibly ask of it. Now, what is the context to the case? The market research team at a company is assigned the task to identify the profile of the typical customer for each treadmill product offered by the company. The market research team decides to investigate whether there are differences across product line with respect to customer characteristics. Exactly what you guys were suggesting that I should do with respect to the watch. Understand who does what. Entirely logical. The team decides to collect data on individuals who purchase a treadmill at a particular store during the past 3 months. Like watches, they're now looking at data for treadmills. And that is in the file, in the CSV file. So what you should have is, you should have a CSV file in the same directory, and through the magic of Python, you don't have to worry about things like path. Before we get there, remember, because we're looking at this statistically, before we get the data, we should have a rough idea as to what we're trying to do. And so they say that here are the kinds of data that we are looking at. The kinds of products, the gender, the age in years, education years, relationship status, annual household income, average number of times a customer plans to use a treadmill each week, average number a customer expects to run, walk each week, on a self-rated fitness scale on 1 to 5, where 1 is in poor shape and 5 is in excellent shape. Some of this is data, some of this is opinion. Some of this is opinion masquerading as data. Like, for example, number of times a customer plans to use a treadmill. Hopeful, wishful thinking. It's still data. You're asking someone, how many times will you use it? Her rows, daily, no problem. 7 times a week. Oh, we'll see. But it's still data. It's come from somewhere. So what has happened, the way to think about this is to say that I want to understand a certain something. And the certain something has to do with the characteristics of customer characteristics. And to do this, you can then use you can either take, let's say, a marketing point of view, who buys. You can also take a product engineering kind of view, what sells, in other words, what kind of product should I make, etc. In business, as you probably know, for those of you who are, any of you entrepreneurs? One hand up. One hand up. They're closet entrepreneurs from what I could figure out. Right. Sometimes it's unclear what that word means. In other words, you think you are, or you're not confident enough to call yourself one, or you're doing that. In IT space, if you're an entrepreneur, for example, in physical product space or even in software space, one of the things you often think about is what's called the product market fit, which is you're making something. How do you match between what you can make and what people will buy? Because if you make something that people do not buy, that doesn't make any sense. On the other hand, if you identify what people buy and you can't make it, that also doesn't make too much sense. So the conclusions that we will draw on this, we will not draw on today. But the purpose is to be able to go towards the conclusions of that kind. Either isolate products, isolate customers, and try and figure out what they tell us. Pandas generally has a fair amount of statistics built into it. That's what it was originally built for. NumPy is something that was built more for mathematical problems than anything else. So some of the mathematical algorithms that are needed are there. There are other stat-sci plots in matplotlib or Seaborn and many other things that you've seen already. Python is still figuring out how to arrange these libraries well enough. Shall we say, the programming bias sometimes shows through in the libraries. So I for one do not remotely know this well enough to know what to import upfront. But a good session, you know what to import upfront and you do all this upfront. So you don't get stuck with what you want to do. The naming is up to you. If you like the names as they are, then that's fine. If you want a standard set of names. So when you wrote the data set, if this is in the right path, just this will work. .csv. It's usually smart enough to convert Excel forms into CSV. In other words, if you have this as XLS and things like that, it's usually smart enough. But if it isn't, then just go in and save an XLS file as a CSV file and operate that way, in case it doesn't do it on its own. But more often than not, what you see is that when Jupyter sees it, it will see any XLS file as a CSV file. Or go and make the change yourself. Or you can have other XLS, other restatements in it as well. You can change functions inside it and you can figure out how much to head. What this tells you is there's the head and the tail of the data. This is simply to give you a visualization of what the data is. This gives a sense of what variables are available to it, what kinds of variables they are. We'll see a little bit of a summary after this, etc. So for example, some of these are numbers. Income. What is income? Income is annual household income. That's a number. Some, for example, let's say gender, male, female, this is a categorical variable. This is not entered as a number. It's entered as a text field. If you are in Excel, for example, right at the top, if you go in and you see that, it will tell you how many distinct entries there are, how many distinct settings there are. So usually what happens right at the beginning, and a data frame like this, if it is created, this is a data frame. If a data frame is created, when it gets created, the software knows as to whether it is talking about a number or whether it is talking about categories. There are certain challenges to that. You can see one particular challenge to this. What does this 180 mean? Counts. Why do you think there are so many decimal places that comes here? 14 years of experience, 16 years of experience. Why is it going 0, 0, 0, 0, 0, 0, 0?
No, that's because mean, median,
by default,
Yes, it does this because it sees other numbers where those decimal places are needed. So what it does is, what any software typically does is, when it sees data, it sort of says that at what granularity do I need to store the data. Sometimes this is driven by your computer, your 64-bit, your 32-bit and things like that. But what it does is, it means that the data is stored in the data frame to certain digits. Now usually you don't see that, you'll see it in this way. But sometimes, for example, when you say include equal to or and you ask for a full description, the data comes out in this slightly irritating way. Because of something here, because of, let's say, the income field or any of that. Now, when it looks at the descriptions of this, what is the description that it is reporting and how does it choose to report out the description? So in this particular situation, so let's take a little bit of a closer look at this. One thing here, look at the way it's done here. So count, unique, top, frequency, and then there are certain things here. Mean, standard deviation, minimum, 25%, 50%, 75% and max. When it sees a variable like gender, it reports out lots and lots of NANs. What does that tell you right off the bat? It can't do that, which means it's not a number. This is not a number. In other words, if you ask me to find the mean of something and you're giving me male and female as inputs, I don't know what to do. Which is an entirely reasonable stand to take for any reasonable algorithm, right? It requires another kind of description for it to work. But the problem with describe this syntax is that it's asking for the same description for all of them. Whether it's in significant digits, whether it's in columns, etc., etc. So it's chosen this description and it says that that's all that I'm going to give you. But where it makes sense, let's say for example I look at age. Now for age I've got 180 observations and it is calculating certain descriptions for it. Correct? So what are the descriptions that is calculating? Let's look at these. It's calculating a description like say minimum. Minimum is what? 18. Maximum is 50. These are easy to understand. Then let's look at something really interesting. Suppose I want to report one number, one representative age for this data set. This is like asking the question, how do I get a representative blood sugar number for you? I can give you a minimum and a maximum, but to do the minimum and the maximum, I need to draw blood many times from you. But let's suppose I want one representative age for you. Somebody asks you, what is your blood sugar? You want to give them one number. Similarly, somebody is looking at this data and asks the question, give me a representative age. How old is your typical user, or what age do you want to build it for? Or you're even asking, let's say, a product question. You're a product designer, and a product designer building a treadmill. Now, how do you design a product? Those of you who are engineers, based on the weight. Now, very good. What weight? Whose weight? Who's the user? What is the weight of the user? He's got a good point. As a design engineer, I need to know what weight will be on that treadmill. Now, what is the answer to that question? Max?
Users who visit the gym.
So there's a question of saying that if I want to measure a variable by one number, how should I even frame that question? What makes sense? What is a one average? No? Max? In this particular case, you might argue the max is the right number, because I want to be able to say, if I can support him, I can support anyone. But there's also a downside to that. I've now engineered that product. You could argue that I have, shall I say, over-engineered that product. Correct? I'm sorry?
Factor of safety.
A factor of safety? Okay. Alright. So let's suppose that you are doing this for a mattress. You all sleep on mattresses. We're all relatively wealthy based on the fact that we're here. So we probably sleep on a mattress. Not everyone's fortunate enough to sleep on a mattress, but let's suppose you do sleep on a mattress. How much weight should that mattress be designed to bear? If you over-engineer it, what will happen is that number one, for a reasonable weight, let's say weight a lot below that, that mattress is not going to sink. Let's say that you design it for 100 kilos. Now if you're 50 kilos or 60 kilos, that mattress is not going to sink for you. Because it's going to feel comfortable for someone who is 100 kilos. And for someone who's 50 kilos, you're just going to bounce on it. You're not going to feel its soft silkiness or whatever it is you want to feel from the mattress. It won't work. So what to do? So that's a hard problem. It's a description, but it's a hard problem. Who do I engineer it for? And so therefore, people have different ranges of what I mean to represent it. So here's one version of it. This is what is called a 5-point summary. I report out the minimum, the 25% point, the 50% point, the 75% point, and the maximum. Variable by variable, I report 5 numbers. I report the lowest. What does 25% mean? 25% of my data set or the people are younger than 24. The youngest is 18. 25% or a quarter of them are between 18 and 24. A quarter are between 24 and 26. A quarter are between 26 and 33. And a quarter are between 33 and 50. This is what is known as a distribution. This is what is known as a distribution. The statisticians love distributions. They capture the variability in the data and they do all kinds of things with it. So I'm going to draw a typical shape of a distribution. we'll make more sense of it later on. This is a theoretical distribution. A distribution, for example, let's say has a minimum, has a maximum, has say a 25% point, has a 50% point, it has a 75%. In terms of probabilities, there's 25% here, 25% here, 25% here, 25% here. If you want to think in terms of pure description, this is not a probability, it's just a proportion. If you want to think in terms of probabilities, what this means is that out of 180 people, if I draw one person at random, there's a 25% chance that that person's weight is going to be below 24. Sorry, age 24, correct. If you want to think in terms of probabilities, we'll do that tomorrow. But this is a description. So what this description does is it gives you an idea as to what value to use in which situation. So for example, you could say that I'm going to use 26 as my representative age. If I do that, what is the logic I'm using? This 25%, this 50% point, so to speak, this is called the median. This is called the median, and we'll see it. Median means the age of the average person. First sort, take the middle person and ask, how old are you? The age of the average person. I could also ask for the average age of the person. Which is what? Which is the mean. Which is 1 over n x1 plus xn. Now this is algebra. What you have to do is you have to put n equal to 180. This is the first age, the second age, the third age up to 180. 1 by 180, age 1 plus age 180. This is called the mean. This value is what? 28.79. The average age is about 28 years or 28 and a half years, 28.8 years. But the age of the average person is 26. Yes?
So could you please repeat the median and the mean?
The difference between the two?
You described what is the age of the person.
So I described the median as the age of the average person. And I described the mean as the average age of a person. Now he's looking at me like saying, you have to be kidding me, right? That's confusing. I admit to it. The easy way to understand it could be this. What is the mean? Add them all up, divide by how many there are. What is the median? Sort them from the smallest to the largest, pick off the middle. If they're an even number, what do? You take the average of the two middle ones. If they're the same, it'll be the same number. If they're not, it'll be a number between them. So sometimes the median may show up with a 0.5 or something like that for that reason. If there is an integer counts, but there are an even number of counts. Now, which do you think is better? You're giving the right answer. It depends. You'll figure out that I like that answer. They both make sense. They both make sense. It depends on what context you're going to use it for. In certain cases, yes.
You said that median is basically the mean of the.
It's the age of the average person. It's a reading from the average person.
So what is the parameter we are saying? It is the average person. How we are getting that average?
Okay. So if you're talking in terms of parameters, so he used an interesting term. He's saying, what is the parameter I'm after? Parameter is an interesting word. Parameter refers to something what generally in a population, it's an unknown thing. that I'm trying to get after. For example, blood sugar is a parameter. It exists, but I don't know it. I'm trying to get my handle on it. Correct? So if I'm thinking in terms of parameters, then these are different parameters. So let's look at a distribution here. I'm not sure whether this will pick up things. I hope so. So the median is a parameter such that on this side I have 50% and on this side I have 50%. This is the median. The mean is what is called the first moment. What that means is, think of this as a plate of metal and I want to balance it on something. Where do I put my finger so that it balances? It is the CG of the data, the center of gravity of the data. You can understand the difference between these two now. If, for example, I push the data out to the right, what happens to the median? Nothing happens to the median because the 50-50 split remains the same. But if I push the data out to the right, the mean will change. It will move to the right. Your lever, the lever principle, right? If there's more weight on one side, I have to move my finger in order to counterbalance that weight. So these are two different parameters. If the distribution, for example, is what is called symmetric, symmetric means it looks the same on the left as on the right, then these two will equal. Because the idea of going half to the left and half to the right will be the same as the idea of where do I balance, because the left is equal to the right. So when the mean is not equal to the median, that's a signal that the left is not equal to the right. And when the mean is a little more than the median, it says that there is some data that has been pushed to the right. And that should be something that you can guess here, because the mean and the median to some extent are what? 24, 26, etc. The lowest is 18. That's about 6 years, 8 years less than that. But what is the maximum? 50. That's 25 years beyond. The data is pushed to the right a little bit. Instead of saying pushed to the right technical term is right skewed. There are, shall I say, people are more not average on the older side than on the younger side. There was a hand up somewhere. Yes.
I was just confused with the statement that median would not move, but then you explained it.
Yes. So therefore, one reason that the median often doesn't move is because it is not that sensitive to outliers. So let's suppose, for example, we look at us and we ask ourselves, what is our mean income or our median income? And we have that. Each of us make a certain amount of money, we can sort that up and put that in. Now let's suppose that Mr. Mukesh Ambani walks into the room. Now what is going to happen to these numbers? Mean is going to go up, right? He alone probably makes a very large multiple of all our incomes put together. Possibly. I don't know how much you make. I know how much I make. But what's going to happen to the median? It's going to stay almost the same. The typical person may move by at most half. Because what is the typical person going to be? The typical person is going to be an actual individual in the room, or maybe an average of 2 individuals in the room. And that person is not going to change. Yes. Yes. That's one conclusion we can draw on this. There are other plots below which will also show the same thing. You're not being able to draw that conclusion. Well, good logical reason. I haven't shown you the full data. We'll see the histogram and we'll do that. So hold on to that question. The conclusion was drawn is that there are two things to do. See here. One is, if I simply look at this without seeing any more graphics, where is the middle of the data from a median perspective? At 26? Correct? Now from 26, look at the difference between 26 and the smallest. 18. Between 18 and 26, that's 8 years. This 8 years contains 90 observations because there's 180 total. Now, what is on the opposite side of this? 26 to 50. That's how many years? 24 years. This 24 years now contains how many observations? Same 90. So there are 90 observations that are between 18 and 26. And there are 90 observations between 26 and 50. So if I were to draw a picture, what would that picture look like? Yes, exactly as you're drawing it, right?
It means what we can say is skewed on the left hand side or right?
This usually by definition is called right skewed. This is a problem that BABI has. Does this mean it's left skewed or right skewed? As a word, right, it's called right skewed. More data to the right. Sorry, more data is a dangerous word. No, it's the same number of observations. I'll say the data is pushed to the right.
More variation on the right side.
More variation on the right side is probably a safer way of putting it, yes. So skewness is often measured in various things. One measure of skewness is typically, for example, mean minus median. Mean minus median, if it is positive, it usually corresponds to right skewness. Mean minus median negative usually corresponds to left skewness. This is a statistical rule, but sometimes it is used as a definition for skewness. There are many definitions for skewness. Skewed data sometimes causes difficulties in analysis because what happens is the idea of variation changes. Being variation on one side means something a little different than variation from the other side. By the way, what's happening to you with respect to things like books? Are you getting books? Are you not getting books? You have no idea what the books are? You got one book, which is what? Which is the statistics book? Okay, I'll take a look at that book later. So, this book, right? Okay, show me the book. Okay. Comment 1, very nice book. Comment 2, not a Python book. Right? That doesn't make it a bad book. So if you're looking for help on how to code things up, this is not the right book. Get a book like Think Stats or something like that. But if you want to understand the statistics side to it, it's an excellent book. So everything that I'm talking about is going to be here. I might talk about which chapters and things like that at some point. And I might talk about how to use this in the book. So for example, at the back of this book, there are tables. There are tables at the back of this book, which we'll learn how to use. And then I'll try to convince you that you shouldn't use them. But remember, many of these methods are done in ways in which either you don't have access to computers, or if you do have access to computers, you don't have them, shall we say, at runtime. In other words, when I want to run the application on it, I can build a model using a computer, but I can't run it within one. The runtime environment for statistics is often done when there are no computers around. The build environment can include computers, but the runtime environment cannot. A lot of statistics is done under that kind of situation.
Even probability is also probably?
Yes, very much so. Very much so. Okay, so definitions of skewness and things like that. Do it in the way you usually use a book, which means you go to the index and see if the word is there. And then you go back and figure it out, and it will give you some ideas as to how that works. It's a nice book. It's one of the best books that you have in business statistics, but it's not necessarily a book that will tell you how to code things up. That is not a deficiency of the book. Not every book can do things of that sort. There are other books around that will tell you how to code things up, but will not explain what you are doing. It's important to know what you are doing. It's also important to know why you're doing it. But books can't be written with often everything in mind. Yes?
Can you suggest some book which tell us how we can think that way?
The thinking is here. I think this is good for thinking. I would absolutely recommend this book on the thinking side.
Because the problem lies that in which situation what we need to apply.
Yes. And that answer I think is very, very good here. Where you won't get is it will say do this, and it won't give you the Python syntax to do it. That will not be here. So if you can solve that problem through some other means. I used to have a colleague in corporate life who had a very big sticker on his board. It said, Google search is not research. Right? Now nobody agrees with him anymore. So I suppose that when in doubt, you do what normal Homo sapiens do today, which is you Google for an answer. So one possibility is that you understand something from a book such as this, and if you want to understand the syntax, just Google for the term. Say Python, that term, whatever, it will probably give you the code. things are very well organized these days. There's also the question, and I should give you a very slight warning here, not to discourage you from anything. But in the next 9 months or thereabouts, the duration of your program, there's going to be a fair amount of material that will be thrown at you. Correct? The look and feel will sometimes be like what we would often call at MIT as drinking from a fire hose. You can if you want to, but you will get very wet. So therefore, pick your battle. If you want to understand the statistics side of it, please go into the depth of it. But if you try to get into equal depth on every topic that you want to learn, that will take up a lot of your professional time. Now the reason we do the statistics first, one, it's a little easier from a computational perspective, although harder from a conceptual perspective, so we begin it this way. But hold on to that idea, and then as you keep going, see if this is something that you want to learn more on. And if you can, you're welcome. Just write to us or let us know, or let anyone know that Hoida just come in, let her know, and we'll get the references to you. But if you want to, say for the first 2 residencies, please read the book and see what happens. If there are doubts, yes, but it's a well-written book. Its instructor is one of our colleagues here. If you want, we can also help explain things. So this is the summary. What did the summary tell you? This summary gave you what's called the 5 numbers that help you describe the data. Minimum, 25, 50, 75, max. We'll see another graphical description of this. It also described for you a mean. There is also another number here. And this number is indicated by the letters STD. STD refers to standard deviation. STD refers to standard deviation. And what is the formula for a standard deviation? STD is equal to the square root of little bit of a mess, but 2 steps. Step 1, calculate the average. Step 2, take the distance from the average for every observation. Ask the question, how far is every data point from the middle? If it is very far from the middle, say that the deviation is more. If it is not far from the middle, say that the deviation is less. Deviation being used as a synonym for variation. I'm talking about variation. Variation can be more or variation can be less. More than the average, less than the average. If someone is much older than average, there's variation. If someone is much younger than average, there is variation. So therefore, both of these are variation. So what I do is, when I take the difference from the average, I square it. So more than x bar becomes positive, less than x bar also becomes positive. Then I add it up and I average it. There's a small question as to why it is n minus 1, and that is because I'm taking a difference from an observation that is already taken from the data. Now I have squared. When I have squared, my original unit was in age. When I have squared, this has become age squared. So I take the square root in order to get my measure back into the scale of years. So the standard deviation is a measure of how spread a typical observation is from the average. It is a standard deviation, where a deviation is how far from the average you are. And because of this squaring, you need to work with a square root. In sort of modern machine learning, people sometimes use something called a mean absolute deviation, MAD, very optimistically called. So what MAD is you don't take a square, you take an absolute value. And then you do not have a square root outside it. And that is sometimes used as a measure of how much variability there is.
So why it is square then?
Why is it?
Why we do it just
We square it because we want to look at both positive and negative deviations. If I didn't square it, what would happen is it would cancel out. What was the word that one of you used? Neutralize, right? I love that term. Your positive deviations would neutralize your negative deviations.
So I went with this x minus x bar is there.
Yes.
So it should be like x square minus x square. And if you are seeing the positive and the negative.
This number is going to be positive if say x1. So let's look at the first number here. So if I look at the head command here, when I did the head command here, what did the head command give me? The first few observations. So now this is an 18-year-old. This is probably sorted by age. This is an 18-year-old, correct? Now I'm trying to explain the variability of this data with respect to this 18-year-old. Why is there variation? This 18 number is not the same as 28. And 18 is less than 28. So what I want to do is I want to go 18 minus 28.7. What I'm interested in is this 10. This 10-year difference between the two. Now the oldest person in this data set is how old? 50. When I get to that row, this 50 will also differ from this 28 by 22 years. So I'm interested in that 10 and I'm interested in the 22. I'm not interested in a minus 10 or a minus 22. I can do that. I can do that. In other words, what I can do is I can represent 18 minus 28 as 10 and I can represent 28 minus 50 as 22. And that is this. As I said, 1 over n minus 1 absolute x1 minus x bar plus absolute xn minus x bar. That is this with n minus 1. And this is done, as I'm saying. This is what is called mean absolute deviation. And many machine learning algorithms use this. You are correct. In today's world, this is simpler. Now, when standard deviations came up first, this was actually a little harder. But people did argue about this. I think, well, 150, maybe more about, I forget my history that much. There were two famous mathematicians, one named Gauss and one named Laplace, who argued as to whether to use this or whether to use this. Laplace said you should use this, and Gauss said you should use. Now the reason Gauss won was simply because Gauss found it easier to do calculations. Why is this easier to calculate with? Because Newton had come up with calculus a century or so before that. And so, for example, let's suppose that you want to minimize variability, which is something that we often need to do in analytics. Which means you need to minimize things with standard deviation, which means you need to differentiate. This function, the square function is differentiable. You can minimize it using calculus. This is not. So therefore, what happened was Gauss could do calculations, but Laplace could not, and Laplace lost. And Gauss won the definition of the standard deviation.
We haven't much used 25% or 75, so
okay. Why do we not do that? So, today, this entire argument makes no sense. Because today, how do we minimize anything? Our computer program. You don't use any calculus. You run fmin or something of that sort. You basically run a program to do it. So therefore, this argument you can both do calculations equally well with this as in that. So today, what is happening is that Laplace's way of thinking is being used more and more. This one is a lot less sensitive to outliers. This one, what it does is, if it is far away, the 22 squares to 484 or something like that, which is a large number. So the standard deviation is often driven by very large deviances. Larger the deviance, the more it blows up. And so therefore, this is often very criticized. If you read, for example, the finance literature, there's a guy called Taleb, Nassim Taleb, he writes this book called The Black Swan and Fooled by Randomness, where he left and right criticizes the standard deviation as a measure of anything. So, Today, this argument doesn't make a great deal of sense, and when in practice something like this makes sense, it's often used. So, a lot of this is done historically. It looks this way because of a certain historical definition, and then it's hard to change. So today, in centuries after Gauss, sad people like me are trying to explain it and having trouble doing it because there's a logic to it, right? I mean, and that logic doesn't hold at all anymore now. Yes.
Standard deviation in simple terms is that VP. How far generally is that from the median?
How far on the average is an observation from the average? Confusing statement again. He's again going to be unhappy. But how far on the average is an observation from the average? If that answer is 0, that means everything is at the average. But you're asking the question, how far from the average is an observation on the average? If I take your blood pressure, how far from your average blood pressure is this reading? If this is exactly equal, then I don't need to worry about variability. Every time I measure blood pressure, I'll see the same thing. What is your average bank balance? Don't tell me that, but you know what I mean, right? You have an average bank balance. Your bank account manager or your bank actually tracks this, what your average bank balance is. But you're not actually, your balance is almost never or very, very rarely equal to your actual average bank balance. It's more and it's less. How much more, how much less is something that the bank is also interested in order to try and figure out, how much of your money, so to speak, to get out there. Because the bank is going to make money by lending it out, correct? But when it lends it out, it can't give it to you. So it makes an assessment as to how much money, I don't want to get into finance now, but you get the drift. So therefore, it is a measure of that. It is not the only measure of that. So for example, here's another measure. So you remember this 25 number and the 75 number that you're asking about? Let's say that I calculate a number that looks like this. Let's say 33 minus, let's say 33 is a 75% point, minus 24. So 33 minus 24, let's say this is my 24 and this is my 33. Between this, how much data lies? 50%. Why? Because this is 25% and this is 25%. This now contains 50%. This is sometimes called the interquartile range. Interquartile range. Big word. Right? Now, why is it called an interquartile range? The reason is because sometimes this is called Q3 and this is called Q1. Q3 stands for upper quartile. You can understand quartile, quarter. So upper quarter, and this is the lower quartile. And the difference between the upper quartile and the lower quartile is sometimes called the interquartile. Why is it called the range? Because what is the actual range of the data? The range of the data in this particular case is 50 minus 18. And 50 minus 18, which is your max minus your min, this is sometimes simply called the range. Range is maximum minus minimum. Interquartile range is upper quartile minus lower quartile. And these measures are used. They do see certain uses based on certain applications. You can see certain advantages to this. For example, let's suppose that I calculate my 5-point summary. With my 5-point summary, I can now give you a measure of location, which is my median, and I can give you 2 measures of dispersion, which is my interquartile range and my range. So those 5 numbers have now been twisted to give me a summary number, which is the median, and a range number. Interestingly, I can also draw mental conclusions from that. For example, I can draw conclusions from these 5 numbers in the following way. 24 and 33 half my customers are between 22 and 24 and 33. So if I want to deal with half my customers, I need to be able to deal with a range of about 9 years. Within this 9 years is all that I'm interested to get this right. So if I'm building my machine, I'm going to make sure, let's say, that the 33-year-old is okay with this and the 24-year-old is okay with this. Will the 50-year-old be okay with this? Yeah, may not be. But if I want to make the 50-year-old okay with this, I'll have trouble with the 18-year-old. So I can do a lot with even these 5 numbers. We'll see more descriptive statistics as we go along. By the way, this is only for age. I can do this for usage, I can do this for fitness, I can do this for income, I can do this for miles. Income is interesting. Here's the median income, $50,000, and the mean income about $53,000. If you see income, in almost all real cases, the mean income is going to be more than the median income. The per capita income of India is more than the income of the typical Indian. Say, what does this command do? If I say mydata.info, what this is doing is, my data first of all is a data frame that I created. Just to review, I read the PDF file this way. Now this is a describe, and this here is info. Now describe and info in the English language are similar things, description and information. This is interpreted in the software as two completely different things. Information is like your variable setting. It's like your integer field, your real field is setting like that. It's giving you information on the data as data. The word data means different things to different people. To a statistician, data means what? To a statistician, data means a number. To an IT professional, what does data mean? Bytes, information. I've lost my data. I don't particularly care what the data is. I've lost my data. So this is that information. It tells you about the data. It's an object. This is description. It's a 64-bit stored integer. It's an object. So it tells you about numeric, categorical. It tells you about the kind of data that's available. Non-null fields. In other words, there are objects in the field, etc. There are so many integer types which are stored at 64 because this computer is probably capable at 64. And there are 3 categorical variables. This is, shall we say, a data object summary of what is there in that data frame, not a statistical summary. Useful in its own way, particularly if you are processing it and storing it. For those of you who are going to go into data sort of curation-like careers, this kind of a database is a nightmare. Because typically what happens is, when you store real data, in addition to data, you often store what's called a data dictionary. Sometimes that's referred to as metadata, data about the data. Because simply storing a bunch of numbers is not enough. You have to say what the numbers are about. This adds a layer of complexity to the metadata. You now have to store not only what the variable is about, but what kind of a variable it is. So many professional organizations say is that archival data should never be a mixture of both numerical and categorical objects. And they pay a price for that. Numerical things should become categorical or categorical things become numerical. But what happens is, if you are storing large volumes of it and archiving it and making it available for people who have not seen it before, it sometimes gets convenient. So therefore, fields like this are often useful to see how big a problem you have. Right? Now I want to plot a few things. To plot, you can plot anything. Simon, I think, is coming a little later. But this plot, this is from Matplotlib library, and it is plotting through a command called hist. Hist means histogram, which you've already seen. You've covered histograms, right? I think you've seen histograms. So this is a histogram. Now histogram as a syntax has bin sizes and figure sizes. So what you can do is you can play around with these and see the differences in what this histogram does. But there's a certain default that shows up, and that default is quite good. And here is a histogram distribution of the age. This is not a set of numbers, this is a picture. This is a picture. What does this picture have? This picture has a set of bins and it has a set of counts within each bins. Between these two numbers, between say 10 and whatever this is, let's say 22 or thereabouts, I have a count of, let's say 17. So it gives a count. And it does this by getting a sense of how many bins there are and plotting this shape. It's a little bit of an art to write a histogram program. There's a Python book out there, I think ThinkStatter one of it, in which sort of the first 1/3 of the book is basically how to write a histogram code. It's a wonderful book, but because it treats this example, it got terrible reviews. Reviewers said, why do I want to learn how to code a histogram? And the book's author is, I'm teaching you how to write a code. A histogram is an example of how to do that. And I tend to agree. If you want to test yourself of your understanding of data and your understanding of any programming language and any visualization language, code a histogram in it. And have fun. So it's a nice challenge from many perspectives. The data challenge, the language challenge, the visualization challenge, all of that. Yes?
So you said archival data should not be numerical plus category.
Many companies do that. That they want archival data to be of only one data form, only one format. Why is that so? Because, as I said, when you store data, how do you store it? Let's say that you've generated an analysis. The analysis is done, correct? And you've decided not to destroy the data. You're going to keep the data in your company's databases or in your own database. How will you keep it? You can take a technology. Let's pick an example. Let's say pick an example. SQL, Excel, whatever. Let's say Excel. Let's say I keep it in Excel. Now, if I keep it in Excel, what will I now do? So let's say I have an Excel spreadsheet. Let's say my cardio data set. Let's say this data set. Now, in addition to the data, what do I need to store with it?
Metadata.
Yes, metadata. How do I store that metadata? Yes, so one possibility is I can have a text file like that, like I had at the top of this, describing all of this, which is typically what happens in Excel storage. It describes this and it describes, there's one file called .dat and another file called .disc or something of that sort, which basically describes the variables, and the idea is that they have the same name, and one extension gives you the data, the other extension gives you the description of the variables that are in this data. Correct? Now this is good. Now what's going to happen? On that data, certain code has been run. That code is going to assume certain things about the data. What do you want that code to assume about that data? Whatever you want that code to assume about that data should be available in the data dictionary. Now, if that code is stable enough to realize that whatever fields you give me, I will run on, that's cool. But if that code requires you to know what kind of data is being used, let's say discrete data, let's say continuous data, in the future you'll be doing things like linear regression, logistic regression. Linear regression will make sense if the variable is a number. Logistic regression will make sense if the variable is a 0 or a 1. If you have that problem, now in the metadata you need to be able to tell not only what business information this variable contains, but also what kind of a computational object it is, so the code can run. So therefore what people often say is that I'm going to make it very simple and I'm going to assume that my entire data frame consists of only one kind of variable, so that when I run any algorithm on it, I know exactly what kind of data input that algorithm is going to get. But I'm saying it's a practical answer that many companies often have. And I've worked in a couple of companies, at least one company where this was very seriously done. So we had to, when we put data back in, we had to convert it. And in the situation that I was in, it wanted everything in categories. So what we would do is we'd take continuous data and we would do what's called fine classing, which means that we would divide not into 4 pieces but into 10 pieces. Decile 1, decile 2, decile 3, decile 4 up to decile 1. And every variable was stored now not in its original numbers but as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So let's suppose that I tell his income is 9. What that means is I know he's in the 9th decile. 10% of the people or more have income more than him 80% have less than him. He's in that bracket. And all variables were stored that way. Now what happens is every algorithm knows that every variable is going to be stored that way. And you can keep writing algorithms that way. Otherwise, what would have to happen is every algorithm would need to be differently. And let's say you're doing credit scoring. Let's say you're doing CRM models. You're doing something of this sort. And you've built a very sophisticated CRM model that tracks your customers. And it works. Now suddenly you've got a new variable coming in, the Twitter feed. And suddenly nothing works. What to do? Go back and rebuild that entire model. That's going to set you back 3-4 months. That's going to set you back a few $1,000s. So you say, no, any variable that has to go in in this form. And if it goes into this form, my algorithm can deal with it.
So, well, in such case, it might not affect the efficiency of the model that we generate?
Yes, yes. And in practice, I'm going far away from topic now. In practice, a professional analyst has to struggle between doing the right thing badly and the wrong thing well. You want to do the right thing well. But the right thing well is going to cost you time, money, data, and everything. So you struggle between saying that I'm going to get a flawed model quickly built on a new data set, or I'm going to get an inefficient answer on a model that's already been built. And let's see how far it goes. And so these are more cultural issues with how an analytical solution is often deployed in companies. They vary very much from industry to industry. They vary very much from company to company, from the culture of a company to a culture of a company. They depend on regulatory environments. In certain environments, an auditor-like entity comes in and insists on seeing your data. Show me your data. Let's say in finance, this is sometimes happening. Regulatory agency, let's say Reserve Bank of India, goes into a bank and says, show me your data. All this NPAs, etc. Show me your order book. Show me your loan book. Correct? And now that has to be done, and the decisions you made have to be done in a way that is patently clear why you have done this. So very often people say, I don't want to make the best risk decision. I want to make the most obvious risk decision. Which may not be the same thing at all. But I'm being audited. So that's a practical question. And I don't have a clean answer to that. But I do know what happens. Is it right? No. It's not. But we live in a world that has that kind of imperfection. One of my teachers, his name was Jerry Friedman. You'll see some of his work later on. He came up with algorithms like projection pursuit, CART, Mars, gradient boosting. He created many of the algorithms that you'll be studying. One of my teachers at Stanford. When he ran our consulting classes, he would say this: solve the problem assuming you had an infinitely smart client and an infinitely fast computer. After you've done that, solve the real problem, where you do not have an infinitely smart client and you do not have an infinitely fast computer. This was in the early 1990s, where computer speeds were a lot slower. And we didn't have powerful machines like this around. So a lot of this is done in that kind of situation, where you are struggling for continuity, when you're figuring it out. Imagine yourself as an analytics manager, and I hope many of you will be. And you have an analytics team sitting in front of you. Correct? You're looking at them and you're looking at them in the eye, and you know how much you're paying them. And you know that half of them are going to leave at the end of the year. What are you going to do with regard to the modeling and things like that? Your first order of business is going to be to ensure continuity in some form. Keep it simple, right? Keep it simple. Keep it obvious for the next bunch of people who are going to come in. And for that, you'd be willing to trade a little bit of, make it right. So, now the new person coming in will now not want to solve a very complicated kind of situation. This is not where you want to be, and I do not want to depress you on day one. But it's also the fun part of the profession, right? It's also what makes it interesting and exciting. Right? It's not all bad. Okay, so the histogram command summaries of what these histograms are, and each gives you a sense of what the distribution is. And as you can see from most of these pictures, most of these variables, when they do have a skew, tend to have a right skew. Maybe education has a little bit of a left skew. Maybe education has a little bit of a left skew, that a few people are educated and most people are here, but even so. Right? Now here's an interesting plot. Matplotlib has this as well, but Seaborn has a better version of it. This is what's called a box plot. You've seen a box plot? This is a box plot. People are unsure as to where this box came from, because there's a statistician called Box who's used this before, but this box came from, it used to be called a box and whisker plot. These are the whiskers. This whisker will go, this is the median. This is the upper quartile, the top edge of the box. The bottom edge of the box is the lower quartile. The end of the whisker is 1.5 times the interquartile range above the box. Right? If you want a formula. Sort of the whisker, the length of the whisker is 1.5 times IQR. Should I have a break now? A little bit maybe, huh? So we'll, okay, 3:45 or whatever, we'll go up to there. Yeah, I haven't stopped, I just got distracted. So 1.5 times the, so it goes up to that. If a point lies outside it, the point is shown outside it. If the data ends before it, the whisker also ends. Correct? What is the whisker? Okay, what is the whisker? Alright, let me explain another way. The whisker is the maximum. The top of the whisker is the maximum. The bottom of the whisker is the minimum. Okay? Not okay. Okay. Some of the points are outside. So, this point here, now what is this plot here? Age for males. So what this means is, this is the minimum, 18 or whatever it is, and this is the maximum, 48 or whatever it is. Minimum and the maximum. So if you see nothing else on the box plot, no other points other than just the box and the whisker, then your 5-point summary is sitting there. That's it. Right. Now, what happens if you see points like this? Outliers. What is an outlier? An outlier is a point that lies more than 1.5 times the interquartile range above the box. So this whisker will not extend indefinitely. It will go up to 1.5 times this box, and then it will stop. And if any points are still left outside it, it will show them as dots. You can treat this as a definition for what an outlier is. Same thing. Same thing in the other direction. The logic is symmetric. No. That means this it hasn't. The data is ended here. The data is ended here.
Was there any other number tried instead of 1.5?
I suppose so, and you can change it. You can. I won't try it now, but you can go to the box plot syntax and change that. So you can go to box plot syntax and you can change that 1.5. It's not hard coded into the algorithm. I think 95% sure. As a statistician, I'm never sure about anything. But it's a parameter in the you should be able to pass the parameter in the box plot function. Default is 1.5. You should be able to change it.
And what's the color part? That's the median, is it?
Which one?
The color.
Color?
Orange color.
Oh no, these two colors? These two colors are because I've asked for two things. I've asked for male and female. If I had 3 of them,
That's okay, but how the range of color? The box.
Oh, this one here? Oh, this is Q3, the lower is Q3 and the upper is lower is Q1 and the upper is Q3.
So this is the quartile range.
Quartile range. So for males, between the bottom whisker to the end of the box is a quarter of your data. The box is half your data, and the top of the box to the end of the whisker is quarter of your data.
So the middle line is
the middle line is the median.
This is the IQ.
The middle line is the median. There is also a function in box plot you can play with where it will give you a dot, and that dot is the mean. I mean, you can ask box plot to do that, but a mean is not a general standard component in the 5-point summary. It's a different calculation, not a sort. But if you want to, you can make box plot to give a dot on the mean as well, by definition. Yes. So mean median. So half the data is between 24 and 34 or whatever that is. Half of all the men in my sample are between those two numbers. I think box plot doesn't allow you to change the shape of the box. I think that is set. That's sort of central to the idea of a box plot. It does allow you to fiddle with the size of the whisker, but I don't think it allows you to fiddle with the size of a box. In other words, if you change that to something else, let's say the 20% point to the 80% point, 80-20 rule, that's no longer a box plot. It's another interesting plot. The significance of it is exactly this, as we had seen before. The significance of it is that the data looks like this. It's right skewed. Think of the picture. So if this is your Q1 and this is your Q3, this is your Q2 or the median, then the median is going to be closer to Q1 than it is to Q3. In the same way that the minimum will be closer to the median than the maximum, same idea. This is a summarization for numbers. If you want to summarize for categorical data, what's called a cross tab or a cross tabulation, this is simply how many products are there. Product category 195, 498 and 798. They've got three kinds of treadmills and they're trying to understand who was using what kind of treadmill. Our business problem is to understand who was using what products. This is a cross tab. What is this? This is something that will be used for categorical variables. No box plot will make sense here. There are no numbers. So now you can ask interesting questions here if you want to, and you can think about how to answer it. Is that, for example, you can ask a question, is there a difference between the preferences of men and women? Possibly. Is there a difference in the products that irrespective of gender, is there a product that they prefer? You can ask all kinds of interesting questions and you can find ways to answer it, which we will do, not in this residency, but next time around.
For those we can categorize it also?
Categorize?
For those preferences?
So this is simply, once again, this is descriptive. All this has done is it has simply told you the data as it is. What I'm saying is that if you want to do a little more analysis on it, you now have to reach a conclusion based on it. So for example, one conclusion to ask is that do men and women have the same preferences when it comes to the fitness product they use? Now that's a question. To answer that question, it's enough to look at the data. But just looking at it will not give me the answer. I need to be able to find a statistic to figure that out. A statistic that does what? That in some way measures that difference. Let's say measures the difference between men and women, or what we will do is not measure that. What we'll do is we'll measure that if there was no difference between men and women, what should this table have looked like? And then we'll compare the difference between these counts and that table. But that's the interesting part of a statistical statistic, which we'll do. That's called a chi-square test. It's coming up in the next residency. But that's the prediction part or the inference part of this description. This is just the description. You can do a similar thing here. This, for example, is for marital status and product. What product you use. Are you not very dependent on whether you're partnered or single? What is marital product versus product? Maybe it has to do with age, or maybe they're correlated. Should you use one as opposed to the other? Okay. You can use counts as well. If you say instead of doing it this way, instead of seeing it as a table, if you want to see it as a plot, you can ask for counts. So there are things like count plots and bar plots, which allow you to do counts. In the lab, you'll do probably a few more of these. This is simply another visualization of the same thing. For those of you who like things like pivot tables in Excel, Microsoft has made, wonders of us all. In corporate life, I was told that you can have a master's in bachelor's and master's in anything. Engineering is good, etc. And it's nice if you have PhDs in a few areas. But what you really need is a PhD in PowerPoint engineering. I mean, that's a necessary qualification for success. So certain tools have been used. So therefore, those tools have been implemented in many of these softwares as well. This is the pivot table version of the same data set. This is the last, not last, but still this is a plot. Let me show you this plot and then we'll end, or we'll take a break. This is a plot that is a very popular plot because it is a very lazy plot. This plot requires extremely little thinking. Pair plot of a data frame. Right? You don't care what the variables are. You're telling it nothing about the plots. You're simply saying, figure out a way to plot them pair by pair. And it does that. So for example, how would you read this plot? On this side, so it creates a matrix. The rows are a variable and the columns are variables. What is this? This is age versus age. Age versus age makes no sense. So what it plots there is a histogram of age. Doesn't like the gap. Nature abhors a vacuum. I suppose Python does as well. So it'll now plot what it should have plotted is age versus age. You're right, it should have been a 45-degree line. But a 45-degree line is a useless graphic, particularly if the same 45-degree line shows up in all the diagonals. So to make a more interesting graphic, it plots the histogram there. This analysis, this kind of analysis sometimes has a name associated with it. The name is univariate. Univariate means I'm looking at it variable by variable, one variable at a time. When I'm looking at age, I'm only looking at age. It's called univariate analysis. It's just a word. Uni as in uniform, same form, unicycle, cycle with one wheel, things like that. Univariate. Unit.
But for the other set of data also, will it replicate the same kind of pattern? If I'm going to give the other set of data.
Another set of data, it will replicate the same nature of the data. There will be histogram here again.
Age and education versus education, this visualization.
So, yes. So, what it will do is, remember that this graph, the nature of the graph, so let's see this. Right? So, where is gender here? Where is gender here? Is it there? Is gender in my data? It is there? So when I did pairs plot my data, What did it do with gender?
It is only 2 variants, so
Yes. Remember in info, when we did info here, remember how it had stored the data? No, not NAN, here. So it had product, gender and marital status, it had identified as objects in the data frame when it had formed the data frame. So now what does it tell you about the command, the pair plot command? Yes, it will ignore those objects. So in answer to your question, if the data frame has been stored, has been captured with integer 64, basically integers or numerics in it, it will plot. If it's only objects, it will probably give a null plot. Yeah.
So how come age is not a
Say again, age is not?
linear line? Why it is not a linear line? Age versus age.
Why like that? This is the histogram, this is the same plot, this plot is the same as, which plot? This one. It's the same as this one here. No, this is not age versus age, this is just age. Age versus age would have been a 45-degree line, but it's not plotting that. It's not plotting that. In the diagonal, it is not plotting age versus age. In the diagonal, it is simply plotting age's own distribution.
With count. Age with count.
Yes, with the count. So what it is doing is, it is essentially running hist on age, on each observation, and putting it on the diagonal. Yes.
What can we infer from the histogram of like 20 to 25 bins?
20, say again?
There is a bin, right?
There is a bin.
So what can we infer from that? From each bin?
From each bin, it's a count.
Count of people in that age.
It's a count of the number of people who are in that age group. Here, this is age. No, this is miles. This is age. This is age. So let's say between here, between let's say 40.5 and 43.5, or whatever these numbers are, there are 3 people. Remember, the histogram is a visual thing. You can data mine a histogram if you want to, which means you can find out what those are, and you can see it inside histogram. Just ask for a summary of that, it will give you what the features are of that histogram. But the histogram is not meant to be used that way. It's meant to be used as an optical device, to see the shape, to see the count. It's an art to do a histogram. If you change the bins a little bit, the histogram will look a little different. So I would suggest that unless you've got a lot of experience in this, or you really enjoy the programming, do not fiddle with the histogram. Its shape will change. I'll show you a little later after the break. Not change the histogram, but what shape is. No, not in default. You can go in and change it on size. But the bin width, etc., the bin width of histogram takes a little more to change. Right? So there is stuff out here. You can find other things in which you can play this. So there are ways to do it. Okay? So quickly ending, we're losing our food. So these different plots, and we'll continue after the break. The rest of it is simply an X versus Y. So for example, this is age versus education.
Let's do a hands-on. This is the same data set. P-Mind and Diabetes data set. Same data set. Shall we do a hands-on on this? Okay. Alright guys, are you all ready? Okay. So if you have access to the code, the first line is matplotlib. We already know what it means. I'm importing from scikit-learn linear model, logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing matplot, SPLT, Seaborn. I use Seaborn libraries for my plots. Especially pair plot comes out very well in this. So I'm going to use this. Train test plot, you already know what it is. numerical Python, and to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating a model is your confusion matrix. Okay, so that comes through this metrics library. We'll see all these things down the line. Earlier, this PIMA diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy, how many times, by the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university, where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column, whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on car MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is, I'm using a numerical Python function isReal. This function is a binary function, it's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is, I'm going to apply this function isReal on all the rows, all the columns of PIMA-DF. Okay, and you see this tilde over here. This is a NOT operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
DF types, that's it. DF types, when you do, it will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, DF types.
What we do if there is a non-numerical?
What we do if there is a We have to go and identify the record, convert that into NaN, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now. Okay, but we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be. Not possible. Zero in plasma is not possible. But you have zero values in blood pressure, you have zero values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay. Let's move on. Do a describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay, right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You're preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously, you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used, which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. To the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make find it too? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I'll refer to, which I'll take you through when we do FMT, model tuning, but right now we're not going to do that. There is a package available, it's called imlearn, but right now we're going to live with this. There's another way of improving the the classification, performing better in the underrepresented class, that is called modifying thresholds. Thresholds. In logistic regression, naive-based, any other probability-based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. All right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
So you haven't treated outliers
Not
or
yet.
the zero values.
Not
So you just
Yeah, on the raw data. It'll take some time. It's fast actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They're overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue class is perfectly, looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
No, but if you correct those zero values,
Still, whatever technique you apply will be same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah? You see the same problem here also. Every dimension you look at it, every dimension has this problem. On none of the dimensions except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every day. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array. Okay, and that array I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. The fit. Once the model has been found, then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this. Okay. I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below, and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way, but whichever way you follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows. Y predict next, this is your predicted values, goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they're very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. 84. There are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay, we call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey, it's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly around. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So the magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is not. Then rest around 15 to 20% goes into fine-tuning a model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this. Shall we move on? You need to learn the tricks of identifying good attributes. Feature engineering, feature selection, and that is where the core lies. 100%. Domain. If I want to predict the time taken to travel from A to B, then I should have the domain experience of what are the factors that can impact the time. That's what the attributes they collected are useless attributes. It's not good attribute. I don't know, but the fact is it's not good data set for classification.
Here we see the diabetic class was all your models were biased towards
non-diabetic.
So we cannot use data.
That is what this imlearn does. Upsampling, when you create upsamples, It actually creates synthetic data out of the underrepresented class.
Is it acceptable practice to do that? Or
You have only one choice. Either accept it or stay with this. No, I'll tell you. On a serious note, it is an acceptable practice. It is an acceptable. Finally, what is important to me is the model should generalize in production. That is important to me. So when we release models into production, the models are not immediately used in production. They are put into alpha test, beta test. If after jacking up the data, if the model is performing poorly in the alpha and beta, I will not release it.
Just like pre-prod.
Yeah, it is.
Just because you don't have enough data in
It's allowed. See, I'll tell you quickly what happens in upsampling. Okay, upsampling uses k nearest neighbors. So what upsampling does is, if you have two classes, this is underrepresented class, so diabetic class, triangles, and non-diabetic, most of them will be non-diabetic, okay? And there is some overlap here, okay? Most of them are non-diabetic class. What this upsampling using imlearn does is, it tries to generate synthetic data out of this. Just one thing, let me finish this. The synthetic data generated is such that it does not disturb this overlap region. It creates synthetic data in these regions. Yes?
But by doing the upsampling, are we not introducing the bias error?
100%, guaranteed. So we are, by introducing the bias error, we are taking away the bias in the algorithm, which is towards the higher class. We are trying to cancel that bias error by upsampling.
So actually upsampling and downsampling is adjusting the bias.
Correct.
We are actually trading the bias.
We are trading off the bias which exists naturally in the algorithm towards higher class.
So are they exact duplicates or?
No, they are not duplicate. They are synthetic data generated using k nearest neighbors. So I take a random point here, then k nearest neighbors. If you use k nearest regressor, for example, you'll sum up these three and give you the average.
In this case, if you use k-nearest, all our stars will not circles.
No, all are stars, but what it'll do is, it's k nearest regressor. So it's going to take the blood pressure of all three, find out the average, give the average to this new point.
So that can be circular.
That can be?
That can be, so there are two classes, star and circle. So if you don't.
It works only on the underrepresented class. It generates synthetic data only for the lower class. So in this case, it will generate synthetic data only for the diabetic class.
So in this case, like if you take this sample and if you decided to upsample our data, at what point we should stop? Like these many samples would be enough. We should not go further.
It will bring both the samples to 100 same level.
So 50-50 you mean this?
50. It will bring it to 50.
Can you give us some pointers?
imlearn. Go and search for imlearn on Google. You'll find that package imlearn. You'll see a lot of reading materials there. But we will cover in detail in FMT.
Okay. So when you do downsampling, it will reduce the records of
non-diabetic. It'll really go.
So either we can go with that approach.
Don't do your manual approach of deleting the data. Don't do that. That will be the worst thing to do. Anyway, coming back to this. So what the next thing which you're going to try is, since all data is numeric, let's convert all this data into what is called standard scale, xi minus x bar by standard deviation, right? And that's what I'm doing here. From pre-processing library, I'm calling the scalar function. So it converts every record, every column of this data frame into scaled data. Same with test record is also convert into scaled. On that, I rebuild my model and relook at my scores. As I said, sometimes we expect miracles to happen, it never happens.
Which type of scaling does it use? Which type of scaling does it use?
This is z-scores, central values. Yesterday I told you, scaling does not impact linear models. So you won't see any impact. There's nothing else we can do. It converts in z-scores, xi minus x bar by standard deviation for every column. Centralize the data to 0.
So we have a few ways. One is either we do up sampling or down sampling. But right now we don't know which is okay. So we need to try with both and see.
Exactly.
But will that really affect if we do it?
100%. It will affect the accuracy of the recall for the diabetic class. 100%.
No, I mean doing it up sampling or down sampling. I think we can go for either choice. Or compulsorily we have to go for both the choice and then.
That depends on how your data is distributed. It depends on that.
Like both and see whichever will be more accurate.
It depends on that. Okay, it's a very subtle relationship with the data distributions in the various dimensions.
So the only solution is
and the threshold management, changing the thresholds. 50% is the threshold, no? So I can say whenever probability is less than 30%, it belongs to red class. Above 30%, it belongs to blue class. I can change the threshold. Right now, by default, it's 50%. If probability of belonging to red class is less than 50%, that means he belongs to blue class. Right now, it's that. So that 50% can be changed to 30% by building wrappers around this model. Number of records is what you have in your data. Threshold is in your sigmoid curves, okay? Sigmoid or any probability-based algorithm. This is my probability dimension, 0 to 1, 0.5. Whenever a function, this sigmoid function says the probability is greater than 0.5, 0.55, 0.56, then it will automatically say that this record belongs to the blue. If it is below 0.5, it will say it belongs to the red. So I can bring down this threshold and I can put it over here, 0.3. Anything over 0.3 belongs to blue, anything below 0.3 belongs to red. So by changing the threshold, I can control the misclassification of the diabetic cases. No, it's not a parameter. You have to build a wrapper around your model. There's no automatic way of doing this. So I'll use a function in scikit-learn. It's called binarize. In case you're very impatient and you want to know what it is, please go and explore this function binarize, B-I-N-A-R-I-Z-E. How using binarize we can control the threshold, explore that. If you're not able to find, I'll tell you how to do that in FMT. All right, now the requirement is there are apparently 3 different classes of wine makers. Okay, and the situation is the way the wines are classified. I wonder if you people know how it's classified. You have specialized, skilled people who actually taste the wine and they give the classification, the quality of the wine. Yeah. So this is one of the most unenviable jobs, or rather enviable jobs, where you get paid for drinking on the job, right? So the requirement is, can you build using data science a model which takes as input the various parameters of the wine and it tells you what the class of the wine is going to be. So I can replace these people with automated systems. That is the objective, okay? So if you look at the data set, these are the columns available in the data, which I have noted from that UCI data set. The cultivator, alcohol levels, malic acid, ash, alkalinity. Honestly, I have no idea about these things, but these are the various parameters available. So when I load this data set and do a df describe once again is used to identify the tails. Look at any of these columns. We'll just look at one. Take your, okay, look at this, interesting. Look at the cultivator is a categorical variable, so don't look at that. Look at alcohol, mean is 13, median is 13. Malic acid, mean is 2.3, it's almost 2. Ash, 2.3, 2.3. Alkalinity, 19.49, 19.5, almost same. So every attribute, the mean and median are almost coinciding. So there is that, to that extent we are safe. Look at the tails. This tail is, sorry, start with this. This is one almost 1 unit. Yeah, it's 1 unit, and the left hand side tail is also 1 unit. This is 2 units. This is almost 2 units. This is 2.5 to 3.5 units. This is 1.3 to 2.2, almost 5 plus units, 0.7 units. Every dimension, mean and median are coinciding, and the tails on the both sides are almost equal size. So looks like most of the dimensions, there is not much long tails or skews. Only one dimension you will see, which is magnesium. Mean is 99, this is 98, a difference of only 1 unit. Central values, no problem. Look at the tails. 10 units. Sorry, this is 18 units. 18 units versus 55, 54 units. Yeah, this tail is very long compared to the left hand side tail. So this is when your central values are overlapping, 98 versus your 99, central values are overlapping, very small shift. That means you have only a few outliers, very few outliers on the right side. Otherwise, the mean would have been drastically pulled to the right side. So 1 or 2 records seem to have outliers on that one particular dimension.
So should we go ahead and do
All outliers have to be handled.
and then means like
Replace them with some different values. Dropping records is the last option. You may have to, but it's last option. The visual way of seeing this is pair panel, and this is the pair panel. I'll come back to this code. I'm looking at the data types here, but I'll come back to the code. Look at the distributions, and I want you to compare this distribution with PIMA distribution. So let's compare this with PIMA, okay? There are 3 classes and hence 3 curves. And look at these curves. They are overlapping. They are overlapping, but you see the difference? What is the difference? Central values are separated apart. The means are not overlapping. And that makes a huge difference in your ability to distinguish the classes. In PIMA, the problem was even the central values are sitting on each other. So the body is significantly overlapping, but central values are separate. So we are in a better condition than we were in PIMA. Look at this column. The blue and the orange are overlapping, even the central values are overlapping. But at least the green is away. So all the columns, this is, I think this is the worst column we have. This is in your data sets, where all the 3 columns are absolutely sitting on top of each other. This one. And this is ash. Okay. Ash, all the columns, all the classes are sitting on top of each other, including the central values. However, because I have other attributes which can help me segregate, I can ignore this. Right? There you go. So in many of the dimensions, 2 classes are overlapping, but as long as the third one is away. So this is what I was saying. If you have a dimension in which the 2 classes are significantly overlapping, small change in shift, but when I combine this with another dimension, the 2 Gaussians, they become linearly separable. So I'm seeing this distribution this way. I'm seeing this kind of overlap. I'll redo this. I'm seeing this kind of overlap. When I use another dimension, in the other dimension also I'm seeing an overlap. But when I put them together, in that mathematical space, the 2 Gaussians become linearly separable. Because of that, linear separability now possible amongst the classes on the dimensions. Look at this dimension. This one, I don't know which one is this. This one is not going to help you separate the orange from the blue. Doesn't matter. as long as I have this dimension with me, which separates orange from the blues. So one dimension will compensate for the other dimension. So overall, these weak predictors put together become strong predictors. Exactly. Overall, these weak predictors put together become strong predictors, and as you will notice when you go down the line, let's look at the data types. We don't have any non-numerical columns here. Everything is numerical. Keep in mind, all algorithms need numerical columns only. Numerical columns could be categorical or real numbers. Come down. So I'm separating out the X variables, independent variables. The target is the cultivator. I'm splitting my data into training set, test set. I'm splitting my data into training set, test set. Yeah, are all of you with me on this? Okay. You can actually download the dataset from UCI if you wish to. This dataset you can download from UCI and run the code. Very good. I'm instantiating the Gaussian Naive here. There are different variants of Naive. This Naive assumes that the dimensions are Gaussian on each one of these, the distributions are Gaussian on each one of the dimension, and we meet that requirement very well. On all the dimensions, the classes are distributed in almost Gaussian ways. Gaussian means looks like normal distribution. So a perfect case for Gaussian Naive. So I'm calling Gaussian Naive here. There are other variants like multinomial Naive and other Naive which you can make use of. So I'm instantiating the model here. I'm going to do the model fit here. This is where our Naive likelihood ratios will be calculated. And then I look at this. On the training set itself, I'm doing a testing. It's giving me 97% accuracy. Why am I doing this? I'll tell you in a minute. While I can also do this model on the test data. Here I'm running the model on the test data. Okay. And in metrics, there is a function called classification report, which gives me all these metrics, recall, precision, everything in one shot. If you're interested, you can separately print the matrix also, confusion matrix. Now look at this confusion matrix. Look at this. Look at the class level recall. Look at the class level recall. Any problems? Hey, Molly, any problems? From SQL and import Gaussian. Okay. All right. Now look at this. There are 3 classes here, 1 to 3. And look at the class level recall. What is class level recall? Accuracy at class levels. Almost 100%. 1 means 100. 95%, 100%. So each one of the classes, it's able to accurately classify with a degree of, this is what we wanted in PIMA diabetes. It's giving us accuracy in wine data set. Okay, I'll talk about this micro average and all these things down the line. We'll talk about this later. Right now, just look at this recall matrix. I've not told you what precision is. And look at the confusion matrix. Actual number of class A in your test record is 23. All of them have been classified as class A. Actual number of records for class B in your test data is 19. It has correctly classified 18. 12, it has correctly classified 12. You are able to achieve this kind of a score in this model, even though the dimensions are overlapping, the classes are overlapping on all the dimensions, because of some dimensions which come together to make strong predictors. So you should understand the difference between PIMA diabetes and this. In both the cases, the classes are overlapping, but there's one very important critical difference. And it's that difference which is making this, right? So you can run the same algorithm, Naive, on PIMA diabetes and see what is the score you get there. Your job here is to select the right attributes.
But here we are not giving the all in.
That this is, you will never get data on a plate when you're doing real life projects. This is only classroom. But when you do sit down and do real life projects, your customer says, suppose a simple example, can you use data science to improve my customer CSAT rating from the current 3.5 to 4.5 out of 5? Can you do something using data science to help me improve my customer rating in my technical support? These are the kind of requirements which will come to you. Data will never come to you. So now your job is CSAT rating, customer rating for technical support. What kind of data you need? Not decide. You have to first guess what kind of data I need. Your domain expertise will help you. If you don't have it, you'll need to have domain experts. So for CSAT rating in customer tech support, what kind of data I'll need? Can somebody go back to the past tickets? Okay, go back to the past ticket. What kind of data you need? Go back to the past tickets. From the past tickets, you collect what kind of ticket, P1, P2, P3 tickets. I need to find ticket classes. Then whether the ticket belong to hardware, software, or something else, I need those things. And various other, you will decide what kind of data you need. The next challenge will be, where will you get the data from? Some data will be available within the organization. Some data will be available outside the organization. Some data will be available with the customer. So getting these stakeholders to give the data to us will be such a challenge. So all your soft skills will come into play. Right? So once the data comes in, you have to first establish the reliability of the data. What if the tech support department has given you data where customer is very happy? They have not shared with you the dirty data. Your model will go for a toss. Those are the challenges which you will face as a data scientist. Once the data comes to you on those various attributes that you have, you will do this analysis using pair plot and other techniques. Is this column good or that column good? Which column should I use to define customer satisfaction? I come from the IT world just like you do, many of you do. We people have done a lot of projects in Java and C and all these things. The project starts with customer requirements, which we turn into technical requirements, that we turn into design requirements, that turns into code specs, coding requirements. That turns into unit testing, integration testing, and finally, then we go for acceptance testing. In acceptance testing, usually it bombs. Right? The reason why it bombs is, we look at data only in the last stage. Then we come to acceptance testing. We ask customers to give us some data. In data science projects, your project will start with data, the project will end with data. Data is the core. You will be revolving around the data sets. So 80% of your effort, estimated effort in data science project, you will see that when you do the capstone project, we'll go and getting the data itself.
So it's usually start with data-driven approach and end with
100%.
And end with data telling stories.
Yes, 100%. Visualization and storytelling from the data. That is what data science is.
So in between that data analysis.
In between the data analysis, feature engineering, feature selections, model tuning, all these things come in. Hey, so please don't make this assumption. In this hands-on exercise we are doing in the class, you're getting all the data from, right? This will not happen in real world. That's why when people come and do capstone projects, many of them want to do self-driving cars. So we have to take them out separately and tell them, hold on. At least a decade of research has gone into building those self-driving cars. You can't do it in 4 months. So when you come to capstone project stage, you're very far away from that. Please sell it to capstone projects with care. Right, guys? Okay. What I'm going to show you is one more thing. Okay. Though this is kind of doing very too early in this for you, but still let me do it. When you build these models, okay, we need to understand how the model is likely to perform in production. Because I'm going to put the model into production, which means I'm going to disrupt many of the processes in production. So the stakeholders in production are going to ask me, what is the performance you expect from this model in production? Suppose somebody asks you this question, what is your answer? Okay, it completely matched with this, what I'm going to cover, because how do you prevent this from happening in production? So when somebody asks you this question, what is the performance you're likely to have in production? We never give point estimates. We never say my model is going to give 78% accuracy or 80%. We always give a range estimate. My model is likely to give me accuracy between 80% to 95%. The moment you give range, that means you're not 100% sure. The moment you're not 100% sure, statistically you're supposed to associate with a confidence level. How confident are you in this range? So usually the confidence level is measured at 95%. So we give a confidence level of 95%. 95% confident that my model is going to give me accuracy between X and Y. But to be able to do those things, find the 95% confidence level for your estimates, we use a technique called bootstrap sampling. In statistics, it is known as sampling with replacements. Okay, and we also use a technique called k-fold cross-validations. So I'm showing you this k-fold cross-validation, what it means, but we'll do this in detail down the line. Look at this. From scikit-learn, import cross-validation score and cross-validation predict. These two functions are available already. Let me explain to you first what is cross-validation. I have this data set with me. Okay, suppose k-fold CV, that which I'm going to use, k stands for an integer number, just like k nearest neighbors, an integer number. Suppose I see k is equal to 10. Usually we take 10 as reliable. What it's going to do is, it's going to break your data into 10 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's going to break your data into 10 equal pieces. Then what it's going to do is, for I equal to 1 to 10, where I is an index, I equal to 1, 2, 3, 4, 10. For I is equal to 1 to 10, fit using 9, test or predict using the left out. So first time when I is 1, it'll take some 9 data sets, do the fit, and it will test on the left out. Then when I becomes 2, it takes some other 9, maybe this 9, do the fit and do the left out. Then it'll take some other 9, do the fit, left out. It'll do this 10 times because you have taken 10, k is equal to 10. Because you have taken k is equal to 10, it's going to break your data into 10 pieces, train on 9, test on 1. And it'll do this 10 times. Train on different 9s each time, test on a different left out each time. When you do this on this particular data set, so I've imported these two. Cross-val score, I've supplied the model to it, the model which I built up, the training set test label, and CV is 10. When I do this, look at the scores I'm getting. First run, it gave me overall score of 92.8. Second run gave me 92.8. Third run, it gave me 1, 1, 92.3, 92. This is all the scores you have got. Average of all these scores is 96.12. So you can expect your model in production on average to give you 96% accuracy. However, we want to give a range. To get the range, you can find out this distribution, 95% confidence level of this distribution, or resort to bootstrap sample. We'll talk about that later in detail, right? So we make use of this technique to find out overall how the performance is going to be in production. 96% average accuracy score I can expect from this model on this data set.
In this process model,
when we do model score, we did train set and train
Yes.
right? We got accuracy of 97%.
On the
train set. But do you think this accuracy is not correct? Because we have.
No, I'll tell you why. Why we did that. No, we did subsequently testing also we did. Look at the line. We have done on testing also. Okay. Why did I do the evaluation on training and testing? Let me tell you this. Okay. With that we'll wind up. This is a very important point, and you should learn this trick now itself. And if you reflect all these things in your projects, it'll be good. Oh, there it is. Okay. Remember we talked about overfit, underfit? Okay. What is underfit? How do you define underfit? Huh? Sorry? Loosely coupled with less dimension. Straight line, curve line, what the hell, hey boss? What is going on? Using what? I want to reach a sweet spot. On the left side is low, underfit. On the right side is overfit. But how will it know whether a model is underfit or overfit? Okay. Guys, let's. Very good, thank you. Huh? Hey, no, enough. Underfit is that case where in training set accuracy is very high. Okay, I'm sorry, accuracy is very low, and in test set also accuracy is very low. Overfit is that case where in training accuracy is very high and testing accuracy is very low. All right. Right fit, this is overfit. Right fit is that case where training accuracy is equal to, more or less equal to, test accuracy. All right. So if I plot a graph of errors, okay, and this is my complexity, then you will see that my training error comes to 0. Especially decision tree will give you training error 0. But this is my training error. I call it training error, TRAINING error. As my complexity increases, training error comes to 0. But you will see that this is my complexity. Okay, I'm increasing complexity in this direction. You will see that the test error is usually higher than the training error. It also comes down, but after some time it deviates back up. You'll notice that the test error also comes down to some point. After that it backs up, it peaks up. This difference, okay, this difference where the training error starts deviating back up, you should stop here. Below this, it's underfit. Above this, it's overfit. In this situation, your model has absorbed all the noise in the training set and become very complex. And when you take that model on the test data, it bombs. Error is very high on test data. Okay? So this point is what you want to check. So whenever you build model, run the model both on training set and test set. If on training set and test set, training is 80% accuracy, test set is 60% accuracy, you are in this region. If training set and test set, both of them are similar to each other with very few difference here and there, then you are probably in this region. Training is also poor, testing is also poor, you are in this region. Underfit region. Oof. So much to discuss. I know it becomes a bit of overwhelming with so much of information coming in such a short span of time. It'll take time, don't worry about it. Take time, take your own time to sink all this in and keep practicing on the UCI datasets. But don't get miscarried by the UCI datasets, as Birendra pointed out. In reality, you will never get such datasets readily available. Never. If you get, you have to suspect it. Okay? That reality will hit you when you do the capstone project itself. The idea is to teach you that reality. All right. So I'm going to stop here. I'm done for the day. Any questions, feel free to shoot. We're stopping a bit early today, but yeah, that's, yes.
You explain the pair plot and what are the inferences we can do?
Pair plot? Yeah, sure, why not? We can do that. For this data set? Okay.
Actually, I have done this project based on that.
Scores have gone down, right? Overall, what is accuracy? Overall accuracy. Yeah, that is what is 76. That's okay. 74, 76, that means it's an underfit region. Both of them are very close to each other. And class level accuracy, diabetes class, recall, what is the recall? Hey, diabetics class, 88. 62 for diabetic class is 62. 55% and 62% is a big jump actually. It's a big jump. So for diabetic class, this NIBASE is doing well because, can you tell me why NIBASE is doing well for the diabetic class?
You told multiple, if it's overlapping, maybe the different
weaker or weaker will go.
In diabetic class, in PIMA diabetes dataset, you notice that there were 3 attributes on which there was a very small separation between orange and the blue on the 3 dimensions. Those weak predictors are helping the NIBASE algorithm over there. Right? So the lesson that we have from this is, which we'll revisit tomorrow anyway, given data set and given problem statement, we never rely on one single algorithm. We always build multiple models. Each model might be different algorithm, and then we average out. That concept is called stacking. If you use the same algorithm, multiple instances, that we call ensemble. So in production, we always put an ensemble or a stack, and the ensemble or a stack will give you a much more reliable result than individual instances will. Okay, let's move on. So let's see this pair plot. There you go. For always first look at the diagonals. Okay. In the diagonals, the first column is the category, the target column. So we can ignore this. This is category of the 3 cultivators, people who cultivate. The next column is the alcohol. Look at the diagonals. This is alcohol versus alcohol. So it makes no sense to give you scatter plot here. So instead, they have given you density distribution on the alcohol dimension. Since we have used this hue color, which means give me separate colors for separate classes, it's showing you the 3 classes. And what is coming out of this is, between classes there is overlap. But fortunately, the central values of these classes, they are not overlapping. No, this is alcohol versus alcohol. This is just distribution of the classes on alcohol, univariate. This analysis is univariate analysis. It's not comparing the dimensions. So it's giving you a distribution of cultivators from class 1, class 2, class 3 on this dimension. How the values of alcohol for class 1 is distributed, how it is for class 2, how it is for class 3. So what this is telling us is the alcohol dimension can be used to separate out the 3 classes. Okay, go to the next one. If you observe carefully, malic acid, what it's saying is the class 1 is distributed like this, the class 1 malic acids are distributed like this, class 2 malic acids are distributed like this, and class 3 is the green one. What we are seeing is outliers here. For the blue class, on this particular dimension, there seem to be outliers. You see a small bulge over here. Similarly for orange, Similarly, for orange also we are seeing bunch. The problem we are seeing for the green one, there seems to be huge range on both sides. Yeah. So green one also seems to be having some extreme values on both sides. That's why the distribution itself is stretched out. So I have to go back to the records and see on this malic acid for each class, what is the problem? What are these outliers and need to deal with it. But right now, in the raw form, the green stands out separately from the orange and the blue. But the orange and the blue class are overlapping. So this dimension may be very useful in separating out greens, but may not be very good in separating out orange and blues. This dimension is your ash. It's relatively the most useless dimension in this set.
You have the outlier. Suppose if you take the outlier, so you have very less spread. It means that it's a very good predictor for the blue this data.
No. The predictive power base is a function of how cleanly these separate out the distributions. The predictive power of a dimension is a function of how cleanly these distributions are separate out. Suppose there was no blue class. This is a very good dimension to separate orange from the green. If suppose there was no green class, this is a weak predictor for orange and blue. This ash, it's a very weak predictor for all three of them. Okay. This alkalinity, if you see, if you look at, if suppose the blue class was not there, then we are in PIMA diabetes case. But at least it's a good separator for green and blue. Right? So individual dimensions may be weak predictors, but when I put them together, they might be able to segregate the three classes properly. And that is what is happening in the dataset. You asked the question, right? How to interpret this? That's what we are doing. The scatter plot makes no sense because we are not building any linear models here. Okay. So scatter plot I'm not referring. So diagonals is important for us. Any other question?
Based on this, we can drop the variables which are less important.
100%. So, maybe by dropping that ash dimension and reducing the cursive dimensionality, I might be able to get more than 96%.
So if you drop the ash and again reason the volume,
I don't know. I've never done that, but you should try it. Maybe you will get it. Handling the outliers might help you in classifying, because outliers, hey guys, all of you this side please. All of you this side. This is a Gaussian naive Bayes. Gaussian naive Bayes expects your data to be distributed like this. But wherever your data distributed like this, if you handle these outliers, you might get better results, right? So if you handle the outliers, both logistic and naive Bayes will give you better results. Because outliers increase log loss in your logistic. So if you handle outliers, both logistic and naive Bayes will give you good results.
But if the cost will come after like one standard
Treat it means? You're talking about outliers. Okay. Don't remove the outlier. Don't drop the records as much as possible. Unless you're lucky guy, you're given terabytes of data. Right? So usually you'll find yourself in a situation where we don't have the luxury of dropping the records.
But in case of breast cancer and all, we don't know the cell radius. If we replace it with median values or something, that's domain specific.
You have to take, yes, good point. You have to have the domain expert with you to tell you whether calculating the radius is prone to error or the perimeter is prone to error. Right? Because there is a strong relationship between perimeter and radius. That's why you're saying that. So it depends on the domain expertise you have. All right. Okay. There's one point which I wanted to say. Okay. this is called data leaks, and guys, with this I'm going to stop. I'll not go beyond this. Be careful about data leaks. I'll tell you what data leaks is. In your exams, if the question paper gets leaked out, obviously we'll score very high. Obviously we'll score very high, right? But we might not have the real knowledge with us. Same thing can happen in modeling. So in modeling, we break our data into training set, test set, right? And we build our model, model dot fit. We do this using training data. There are various ways in which the test data can leak into the fit function. One of the simplest way you can do this mistake is where you first take the data, you convert this data into z-score, and then you split this data into training set, test set, build your model on this. Why? Because z-score is xi minus x bar by standard deviation. Xi minus x bar by standard deviation is a z-score. This standard deviation is a result of all the records put together. Right? Now, when I break this data into z-score data into this, the test data has already been influenced by the training set. But the test data in no way should have been influenced by the training set. They are not independent of each other. This is a very common source of data leaks. In the classroom, it's okay, but you cannot do this in your projects. Then what will happen is, your model will perform well on test, but it will bomb in production. That is one very common way of data leaks. So whenever you do transformation of your data from raw to this, if the transformation involves all records put together to find your standard deviation, something of that sort, don't do that. Always break your data into training set, test set first, then do the transformations.
I think we did this for this.
Which one?
First Python notebook which we did, right?
We'll do this mistake in entire all the Python notebooks. But you please be aware of this, don't do this in your projects. The second thing I'll tell. Second problem statement is, we talked about one-hot coding. We talked about one-hot coding, right? Look at this. You have in your data set a gender column which has male, 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 females, females, okay, males. Always convert the one-hot coding first so that it becomes gender male, gender female. This will become 10 10 10 0 0 1 0 1 0 1 1 0 1 0. Okay, all of you got it? Then you break your data into training set, test set. This is okay. Training, test. The reason why this is okay is this record has not been influenced by any other records. The records don't influence each other. The transformation of records from here to here is independent of other records. So this is okay. Okay. If you do this transformation after breaking your data into training set, test set. I told you in z-score, you first break your data into training set, test set. Okay. Then first do z-score on training, then do z-score on testing separately. If you do this one-hot coding after breaking your data into training set, test set. Now I break this into training set, test set. What's going to happen is, in your training set, you're going to have only one column, GM, 1, 1, 1. In your test data, you're going to have two columns, GM and GF. This will be 0, 1, 0, 1, 1, 0. So your training data and your test data will not match in terms of the attributes. So whenever you're doing transformation, if the transformation is something which is done record-wise, do it first, then break your data into training set, test set, especially one-hot coding. Otherwise, you'll end up in runtime problems. If you're doing any transformation which involves all the records put together, like calculating standard deviations, then first split it, then transform it. Otherwise, your data will leak.
Here, number of observations will get changed.
Yes, yes, you are. The moment you add dimensions, you're going towards higher complexity of your models. So you're decreasing the bias error but increasing variance errors. So if you create one-hot coding out of a column where the cardinal values, the distinct values is 50, you're going to end up with 50 new columns. So imagine from lower dimensional space, you're going to such a high dimensional space, and your data points is also not very high. You'll end up with a very complex model. So you'll end up in overfit zone, variance errors.
So why we need this? We can still use 0, 1 as the value for.
Algorithm will think that 1 is greater than 0.
Here, if we have 3 categories, A, B, C, and we do level encoding first, so it will convert to 1, 2, 3. In this case, it might think that C is a higher priority than
It will.
So what will do? It will do one-hot.
Yes.
Now it will convert to 0, 0, 1, 0, 1, 0 as per the sequence. So in this case, if we drop one of the variables, the variance will also decrease, and we can predict that if it's 0, 0, then maybe that variable will be 1. Yeah. So we can use that way also to reduce the variance.
Yeah. Okay. One last point. Last test point. This we have been saying since last 3 points. Whenever you create one-hot coding, for example, in this case, you are creating collinear columns. Columns which influence each other. The presence of 0 here tells me that this column will be 1. So I'm able to predict the value of the other column based on this column. So you're introducing collinearity over here. To address this collinearity problem, when you create one-hot coding, we might drop one of the columns. So 0 means male, 1 means female. So I get that information from here itself. I don't need this. So when you do one-hot coding, you're introducing multicollinearity. When you bring multicollinearity, you know what problems exist, what problems happen, you know that. So we might have to drop some of these one-hot coding columns to remove the multicollinearity. We do that.
Again, it has 0, 1. Again, same issue. One is
The purpose of one-hot coding is
One-hot coding does not introduce any order. It just stores it as a label, 0 and 1.
So we can also convert the gender column as a category column at 0.
Unfortunately, when you do that, when you use pandas data frame categorical function, it actually says that it is ordinal values. It has order in it. Discuss the steps and then we'll move on. We'll use a new data set on which I'll run KNN, regressor, then linear regressor, and we'll compare the two. How I used clustering on AutoMPG data set. Let's see that. So let's start with this. This is called car-mpg.csv. Let me tell you what this car is. This data set is about second-hand cars. Okay, these second-hand cars include cars from Europe, US, and Asia. The problem requirement was, can I, looking at the attributes of the car, the horsepower, the weight, the acceleration, and all these things, can I guess what the mileage of the car would be? And based on the mileage, I put a price tag on it. That is the objective. Okay. But that is the objective for supervised learning method. So before we even do that, I want to explore the data and see what kind of information is hidden inside this, which I can make use of, leverage on to build my models, to predict the mileage. That is the objective. So right now we are not going to build any models. We're just going to explore. All of you are aware of this. This linear regression is what my objective was. But when I built my linear regression on this model, on this data set, can I take the liberty of scrolling through? Okay. So when I built the linear model on this, all this is basic statistics, taking care of horsepower column. There are non-numeric values there. All these things is that. come straight down. I can't see it from this angle. Okay. Now this is what I wanted to do. I did a clustering on this data set. Okay. But before I do the clustering, I was just analyzing my various dimensions on this data set. Have you seen this data set earlier? You have seen this data set earlier? Can you all please confirm you're aware of this data set? Yes, no? Okay, fine. So if you remember, in this data set, we had the MPG column, cylinder column, so on and so forth, right? This is what I was telling you. Look at the cylinder column. If you expand this, you'll see a Gaussian here. This is kernel density estimates. Now in this kernel density estimates, we are getting 3 clusters over here, 3 Gaussians. Of course, I've given the color based on one of the dimensions. I think it's called, I've given the color based on origin. Origin is the America, Asia, Europe, okay? So that is a natural cluster in the data set where cars from America, Europe and Asia, they form 3 clusters. So those 3 clusters are visible here, okay? And if you look at the dimensions, in some of the dimensions, you see more than 3 clusters. Within the blue cluster, within the blue, you're seeing 3 subcategories. This is what I was telling you. Within the category, there are subcategories which is visible here as overlapping each other. And these are the 2 clusters based on origin. Look at this. Within the red cluster, again, there are 2 subcategories on this dimension. So the number of clusters in your data set is not likely to be 3 in this particular data set. Okay, though naturally we think it should be 3, but when you club those data sets on the various attributes of the car, you might get more than 3, right? Because we are seeing subclusters over here in those 3. Okay, let's move on. With this impression, I went and did my k-means clustering. In k-means clustering, I gave a range. I said, look for number of clusters 2 to 6. I guessed the range based on my analysis of the dimensions. So when I did this, based on the range, I created the clusters and found the inertia of the clusters, the sum of inertia. I did a plot, okay? The plot comes out like this, elbow plot. Are you all comfortable with elbow plot? I mean, how to make it, how to build it? Okay. Now look at this. This is what I was saying. Though naturally there are 3 clusters in the data set based on origin, the elbow plot is telling you something else. The elbow plot is telling you the drop in error in 4 clusters is much severe. You can't ignore this than in 3 clusters.
I think you drawn X, Y.
Oh, this is my errors?
No, I think it is.
No, 27,000. 27,000.
Okay.
20%.
Okay, what are you talking about?
The scale.
Scale, okay.
1 to
okay. Sorry, this is my error, inertia. This is number of clusters. Okay. So number of clusters here, though logically should have been 3 natural clusters, but what k-means clustering is telling us there are 4 clusters in your data set. Right? So we go and build our 4 clusters here. Look at this. So I'm going to build 4 clusters. And when I build the 4 clusters, look at the output. This is cluster 0 centroid, cluster 1 centroid, cluster 2 centroid, 3 centroid. Are you comfortable with this? All of you? What are these values? The position of the centroid in the various dimensions. That is what this is, okay? So each row is 1 cluster, 0, 1, 2, 3. When I did this analysis, I put all these dimensions in your data frame, and so that it becomes easy to understand. So cluster 0, centroid is located on these attributes. Okay. When I did this, and then now look at this. What I'm doing here is, I'm taking the data sets back. All the original raw data, I'm taking it back, and I'm sending it to the cluster.predict. What this cluster.predict, it's deceptively like modeling. This is not modeling. This is not predicting anything. All the records, they are being assigned to different cluster IDs. K-means clustering has assigned it. Now I want to store back the cluster IDs back into the records itself. That's what is happening here. So in the data frame, we did not have any column called centroids. Now what this is going to do is it's going to create a column called group. In the group, it's going to store the cluster IDs. So I'm creating a new column called group. The group column will tell me which cluster this particular record belongs to. That is what the predict function is doing. It takes as input the records, tells you which cluster it belongs to.
So can you please explain elbow curve once again?
Yeah. In elbow curve, I should have actually labeled this mistake. This is my inertia. Inertia means the sum of variances within clusters all summed up. Okay. So this is my objective function. I want to minimize this. What you see on the bottom is the number of clusters. K is equal to 2, K is equal to 3. You can't have fractions. So K is equal to 2.
That is why actually I was confused. 2.5.
This 2.0 is it?
This is 2.0 because I gave the range as 2.
Okay. So this does a scale you have set like this, but it would be in the full 2, 3, 4 like that.
It can start from 1, but 1 will be the highest errors.
Okay, and 3 to 4, if I see then the shift is too much. And it's a significant shift.
Yes.
That is why we are going for 4.
Yeah, even though in the pair panel we saw 3 natural clusters, but within a cluster we saw subclusters. That is what is coming out here. So 4 seems to be the likely number of clusters you should look for.
So you told, right? So by KD, we roughly can get idea how much of cluster we have. So the range which you have given, accordingly you will.
Yes. Shall we move on? Okay. Now look at this. I got my cluster ID stored inside the data frame. Now how do I make use of this? Okay. So what I did here is I stored back the cluster labels into the records. Which record belongs to which cluster label? Okay, that's what I'm doing at this point. Once I've done that, then I make use of my pair plot, make use of my box plot. So in the box plot, what I do is on every attribute, so if there are 8 attributes in this data set, on every attribute, I do a box plot by clusters. So when I do this, look at this. On the first dimension acceleration, there are 4 clusters with many outliers. You're all familiar with box plots. Okay. Now, whenever box plots are overlapping, the bodies of the box plot are overlapping, that's not a very good sign. It's not a good sign. You will not be able to interpret these 2 clusters separately. They will not come out as distinct clusters. They'll have similar properties. Okay. And because when you look at this dimension from this angle, this is acceleration z scored, you will see that there are 2 humps here. This is a separate hump, 2 humps, and this is a separate hump, 4 clusters. Okay, so not a good situation to be in, but let's move on. This is your cylinder, it's an integral column, so box plots is coming out as simple lines. This is displacement. Once again, the clusters are overlapping. It's not coming out very strongly as distinct clusters, right? Maybe it's a 4 clusters. If I restrict myself to 3 clusters, these 2 might get clubbed into 1, these might get clubbed into 1, and I might have distinct clusters. Even though k-means cluster is telling you 4 is the right number of clusters, right? Let's see, we don't know. But there are many outliers here. Outliers indicate loose clusters. Outliers indicate the data points lying on the edge of the clusters. They're making your clusters very large and loose. So we handle the outliers. I removed the outliers here. All I did is any data point which is lying beyond 2 standard deviations, there you go. I replaced it with a median. Go into your data frame, look at the records cluster wise, sort them cluster wise. Any data point which is lying more than 2 standard deviations within the cluster, replace it with the centroid of the cluster. That's what I'm doing here. When I do this, Now when I form the box plot again, your outliers are almost gone with few outliers. Those of you are not probably familiar with this. I think I've told you this in the class. Whenever you have a distribution, and in the distribution you have data points in the outlying regions, you replace them with median, your distribution becomes sharper, your standard deviation falls. As a result of that, data points which are earlier not outliers, they start appearing as outliers. So you will never be able to completely eliminate the outliers. They will always be there. As long as I've handled the first iteration outliers, I'm okay. So I'm going to ignore the second iteration outliers. Okay. Now when you do this, look at your boxes. Again, the boxes are almost overlapping. These two are overlapping. These two are distinct from these two, right? So my box plot was not really helping me out with 3 or 4 clusters. Even 3 clusters had the same problem, which means the dimensions are not helping me separate out the clusters properly. What I did is, I went ahead and did an analysis using scatter plot. What I did is, I took one of the dimensions, say for example, horsepower. The target variable which I have to predict in my supervised method is MPG. So let's do a plot between MPG and horsepower and see what the scatter plot looks like in these 4 clusters. Now this is where the information will come out. Okay, look at this particular plot. What do you think this green cluster is? This is horsepower. So what do you think this green cluster is? What do you think this red cluster is? Green is large cars, heavy cars, very high horsepowers. These are probably your Maruti 800s, the small cars, very low horsepower. Mileage is very high, mileage is very low. All of you okay? Now look at this. What is coming out of this analysis is, when I look at the green cluster, your horsepower is not a very good predictor of your miles per gallon. The line is almost horizontal. The slope is almost 0. The slope is almost 0. In case in orange also, the slope is much worse. So your horsepower is not going to be good predictor for mileage for orange color cars. Orange cars is your sedans. Whereas if I go for small cars between horsepower and miles per gallon, there seems to be the kind of relationship I expect, a negative relationship and very strong coefficients. Are you able to get it? Do you understand how we are able to extract information out of clusters? Let's see this further. Look at this. This is your miles per gallon with displacement. Not as bad as in the earlier case, but once again for large car, this dimension is a weak predictor. But for small cars, it comes out to be very strong predictors. So when I'm building a model, instead of building one single model to predict the miles per gallon of all the cars put together, which is silly, I'll build separate models for small cars, separate for large cars. And when I build those models, I will not use the same attributes. The attributes I use to build linear model for large cars will be different from the attributes I use to build the model for the small cars. Right? And if you analyze this, one of the worst dimension is your acceleration. This is a horizontal, almost horizontal, and this fact comes out in the pair panel also. Acceleration is a useless column. So if you look at any value of acceleration, you'll find all the cars available. Large cars, small cars, every car is available. And if you look at the pair panel, in the pair panel, look at the acceleration column. Where is acceleration? This is acceleration? Where? This is acceleration. All the clusters are overlapping. So useless dimension. So k-means clustering, I'll show you one more example of how I used k-means clustering. This is for tech support analysis. I hope I have the data with me, the code with me. What I realized is I had to build individual models with different dimensions. So I was getting tempted to try out. This is a linear model. Somewhere down the line, support vector machine didn't help much. It gave me 87% only. I used decision tree. Linear, regression, ridge, and lasso, none of them helped. They're still giving performance in the range of 70s only. But decision tree came out to be better risk. Oh, it's not there. I removed it. What an idiot. Decision tree gives me almost 90% accuracy in prediction. But looking at the output of this clustering on the various dimensions, I took a call that if I build a linear model, I have to build separate linear models. But if you want one single model, decision tree regressor came out to be the right fit. It gave me an accuracy of 90% almost on test data. You want to explore this? You want to try this out? Would you like to take this as a, yeah? Go and explore this. I have not built the linear models. Go and build the linear models on one cluster and see what the performance is. How it can be used in particular case study, it was used to suggest ideas for improvement of customer satisfaction on technical support. I realized I have overwritten that with another code, though the name of the file is still tech support analysis, but it is not tech support. So I'm going to share this code with you. Just walk through the code, you'll find it easy to understand. If you have followed me on the miles per gallon dataset, you'll be able to understand this particular example, okay? So shall we get into hierarchical clustering? Shall we look at hierarchical, all of you? K-means clustering, though very powerful, very commonly used technique. As you would have understood, it requires a lot of thought process, a lot of understanding of the data before you implement it. And one of the challenges of k-means is how do you know how many clusters to look for? That is where this hierarchical clustering becomes handy. Hierarchical clustering gives you a visual way of finding out how many clusters are likely to be there in your data. But at the same time, I must caution you, hierarchical clusters, though they may show visually some clusters in your data sets, those clusters may not exist. How encouraging. Those clusters may not exist really. Okay, so we need to be careful. There are ways of preventing ourselves from falling into such potholes. So we'll see how we can prevent ourselves from getting into these traps. What are the ways in which we can do it? But before I go there, in k-means clustering, you find the similarity or dissimilarity between data points, for which we use Euclidean distance. All of you comfortable with that? Okay. When you come to hierarchical clustering, what happens is we are going to see agglomerative, that is bottom up. Every record, every data point in your mathematical space is treated as a cluster. So in the next iteration, two of these clusters are coalesced, are joined together to form a larger cluster. Which cluster to join to form larger clusters, that is decided based on the distance between the clusters. Once again, the same rule applies. Closer the clusters are to one another, more similar they are. So I want to combine similar clusters into larger clusters. Okay, but the problem is, when you start looking for similarity between clusters, a cluster is no more a one single data point, it is a combination of data points. So the distance calculation between clusters to find out which are more similar to each other, that becomes slightly complex. It becomes complex because there are different ways of doing it. So the different ways of doing it is shown here. One is called single linkage or minimum linkage. Imagine you have three clusters, blue cluster here, yellow cluster, and red cluster. Okay. Now I want to find out which two clusters are closest to each other. what this single linkage method does is it finds out the distance between 2 points which are from different clusters and nearest. So it finds out the distance between red and yellow, red and blue, yellow and blue. Of the three, red and yellow, this distance is the least. So it combines red with yellow. This is called single linkage method. If I look at max linkage, it finds out the distance between the farthest points from the different clusters. Red and yellow, red and blue, yellow and blue. And it takes the one which is least farthest. Always it will take the least. Once again, it might combine yellow and red. Or average distance. Average distance is pairwise distance between all the data points here and all the data points there and their average. Do this amongst red and yellow cluster, red and blue cluster, yellow and blue cluster. Combine those two clusters whose average distance is the least.
Will you do partial combination?
What do you mean by that?
So let's say a few points are closer. Will it shift those points?
No.
The reds will become yellow.
No.
Let's say for that single linkage.
Red and yellow will become one larger cluster with maybe different color, representing both of them. Right? So this has to be done across all the data points of yellow, all the data points of red.
Will it be an iterative?
Which one? All of them are iterative, yes. Iterative means, what do you mean?
But finally, when all the points will merge, or how can you tell that there will be distinct points?
You're talking about this one?
Yeah.
Okay, come on again.
So you are iterating, right? And you start merging it.
No, I'm not merging. I'm just calculating the distance right now. So suppose there's a blue cluster here. Any questions?
No.
Hey, no. Suppose there's a blue cluster here. Let's do this. Okay. Now there are 3 clusters here. 3 clusters. Find out the average distance of all of you from all of them. Find out the average distance of all of you from all of them. Find out which average is the least. You merge with that cluster. So these two become one larger cluster. Right? Obviously, average distance of these points from those will be very high compared to these two averages. So I have not considered that. That is what this average method is.
No, what is the minimum limit it will set to maintain the cluster?
Minimum.
Is it 2, 3, 4?
All the data points will become one cluster.
All the data.
All the data points. Suppose these two clusters are closest than that, all the data points will become one big cluster.
But this would be little risky that it is taking everything, in one go. It is not going point to point, it is taking the whole group and merging the whole group.
Isn't that a better way? Because you're taking more variance in your data set to decide which one to cluster.
But what about the boundary points? Those will, create the issue.
No, they will not. So in this case, the boundary points is those two, and these 3 are the boundary points in these 2 clusters. When you merge, they still remain the boundary points in one large cluster. So all the data points put together become one big cluster, super cluster. It doesn't stop. Hierarchical clustering doesn't stop. It stops at that point where you have no more clustering left. Just like in decision tree, the root node, where the entire data frame is a root node, in hierarchical clustering, it stops only when it reaches the root node, where all data points become one super cluster. They need not be. They need not be. I'll just come to you. Just hold on. I know where you're coming from. Yes, ma'am.
In the first example, so you pick those two, which is the closest. So red and yellow is the closest.
Yeah.
Now, if you had picked the red and yellow in the furthermost, so that means distance between red and blue or red and yellow.
Not this blue. The farthest point of the blue. I'm not showing the blue cluster here. The farthest point of blue.
Yeah, so if we had considered 2 other points where red and yellow is far and the distance between red and blue or yellow and blue is
Yes.
smaller,
They would have
then
merged.
they would have merged.
They would have merged.
So then how it will come on the final one? So that means.
Okay. Since the same question is coming from multiple angles, let's take tackle this. So what's happening is, okay, you have 3 clusters. Let me show with triangles and 3 clusters and something of this sort. Suppose I'm using single linkage method. I compare the nearest points. Obviously, this is the least. So I merge these two into, this is one cluster, this is one cluster, this is one cluster. I merge these two into super cluster. When you merge 2 into super clusters, the subclusters don't lose their identity. They don't lose their identity.
In this example, you show that only where 3 clusters are there. In reality, there can be
many, right? And then he asked me, where does it stop? The clustering will stop once all the data points have become part of one single large supercluster, and there's no more data points left to cluster. So this supercluster is your root node in decision tree. The 2 subclusters is the 2 branches. Within this branch, you further have subsplits. So what you're seeing here is decision tree. Decision tree is formed based on entropy and Gini. Here it is formed based on this distance between clusters. Did I answer your question? No, I didn't. Again, okay, repeat the question again.
So in this, if we see, then what is the point of the cluster at all?
Just
so
wait.
If we are coming up with the one single cluster.
No. Just wait. We'll see the point. Yes.
So you are taking the average linkage, you are taking the average distance, right? So how it will be different from the centroid? You can directly take the centroid distance.
No, not necessary. Not necessary. The pairwise distance between these clusters and these, they need not be same as centroid distance. They need not be same as centroid distance. That depends on the distance calculation method you used. He's asked me a very important point. This is slightly slippery because it's mathematical. He's saying average distance of the data points here from here, should they not be same as the centroid distance? Because centroid is the average of the 2 clusters. It depends on the distance calculation method you use. The distance calculation method should satisfy the triangle of inequality. Do you remember in distance calculation method, I remember doing this in k-nearest neighbors. There are 3 properties that the method should meet. One is distance between point and itself should be 0. Distance between 2 points cannot be negative. At that time we were laughing, we thought it was silly. You remember all these things? So it's not guaranteed, that's what I'm saying. If you use cosine distance violates that requirement of triangle of inequality. So it can't be guaranteed to you that it will be same. Shall we move on?
Yes. So when you say between A and B, right? So you saw the distance between these 2 in the single linkage, the A one.
Single linkage.
You these 2.
Correct.
The distance was smaller.
Yes.
The second one, you're saying complete linkage, maximum distance.
Yes.
In the same example, can you show that?
Yeah, sure. So it's a single linkage. We look at, say, max linkage or complete linkage, where what it'll do is it'll find out the distance between this point and this point, find out the distance between the farthest point here and here, the farthest point from here and here. Of these 3 farthest points from different clusters, which is the shortest? Those 2 will get, coincidentally in this case, it's the same cluster, these 2 will get clubbed.
So if it is very similar, this is the third one, very similar to decision tree. So in decision tree, we get some nodes which we need to prune. So in a similar manner, we will go for this technique also.
Pruning?
Yeah.
We don't need to prune. Why? We'll see that. We'll see. Okay, we'll see why we don't need to specifically do pruning, but we'll see what happens. Right? Still some more length to go before we discuss those
Just
points.
one question
Yes,
for the
please.
classification.
Mhm.
First, we have already done the classification, correct? The
Clustering.
First, I asked a question. Will the red become yellow? Based on this, because there are two things going on.
Correct.
First, we have classified. Next, we are trying to kind of build that tree. As part of building the tree, are we going to be smart enough to, again, reclassify?
Yeah.
Yes, we are.
In fact, that will be done by the algorithm. The classification, what you're talking about, I know what it's talking about. Let's see how it does that. Shall we? Okay. Let's start with distance matrix. All these algorithms make use of what is called a distance matrix. Distance matrix is nothing but very simple stuff. It's a square matrix. Suppose in your original data set, you had these many records, A, B, C, D, F, G. Okay. And now I'm going to find out the distance between each point in the mathematical space from the other. Distance of point A from point B is 0.5, 0.42, 1, 0.25, and so on and so forth. Let's imagine that this distance calculation is done based on Euclidean distance. Are you all okay? So A and B are 0.5 units away, A and C are 0.42 units away. In case you're unable to connect, what I'm saying here is, I'll just do it between A and B. Distance between point A and B is nothing but the distance on x-axis, distance on y-axis, these two, x square, y square, this is under root of x square plus y square. I'm talking about this distance. Okay, so this is what these distances are. Imagine we are using complete linkage. There are different ways of combining clusters, so I'm going to use complete linkage. Okay. When I make use of complete linkage, it looks for the least max distance between points. Okay, so when you start for the first time, given these distances between the data points, the least distance is 0.2. So it combines F and B and makes them into one cluster. So in the next iteration, the distance matrix becomes BF and rest of the data points. The B and F, they lose their identity. BF becomes one single data point. It's a one cluster, right? Why did you combine them? Because they're similar. So if you combine them, they lose their identity. So BF is now the data point. Now the question is, between BF and say point A, how did this come to 0.62? How did it find 0.62? Correct. Look at the distance in B and A, F and A. In the original matrix, look at the distance with B and A, 0.5. F and A, 0.6. You went for max linkage. So it took the max distance. So between BF and A, the distance is 0.62. Similarly, between BF and other data points, it takes a max distance. Are you all okay? Now look at this. This is called dendrogram. The beauty of hierarchical clustering is it gives you a visual interpretation of what's happening. B and F data points, they have been clubbed together at a distance of 0.2. At distance of 0.2, they have been clubbed together into one. Which means if I look at these 2 points from a distance of 0.2 units, they look like one single point. Right? So these two have clubbed into one at a distance of 0.2. This is called the dendrogramic distance. Okay, you'll understand the importance of this down the line. So this is called dendrogramic distance. Now, in this matrix, where BF is appearing as one single point, now which is the closest cluster to, which are the closest clusters here? If you look at this analysis, the closest clusters come out to be E and A. So E and A get combined and they form one cluster. And both the point E and A are replaced by this cluster called AE. Dendrogramically, the point A and E, they get merged at a distance of 0.1 to somewhere 2 point whatever it's 0.25. 0.25. So at the dendrogramic distance of 0.25, A and E appear as one cluster. Once again, apply the max linkage, find out the distance between A and E in other points. Let's look at the distance between AE and BF. What you have to do is you have to see the distance between AF, AB, EF, EB. You will take the max linkage is 0.778. Right? 0.77. So this is my new distance matrix. Once again, look for the least distance. When you do this, you will see that all the individual data points are being replaced by clusters. Then clusters get replaced by superclusters. So AE and CG get merged at a dendrogrammic distance of 1, 2, 3, 4 point something. 4.2.
So actually the previous one, when you were combining the AE and BF, at that time you said that you have to compare E with B and A with F. The
A with F, A with B, E with F, E with B. See which distance? All four here. So I get my this cluster, and finally I end up with a decision tree like a structure where horizontal axis, x-axis represents your data points. What is important to us is the dendrogrammic axis. Some people show it vertically, some people show it horizontally. Okay, next slide, if you see it's horizontal. Doesn't matter. The important point for us is the dendrogrammic distance and the looks. What's happening here is at low levels, okay, these data points are individual clusters, but as we move up in the dendrogrammic scale, the data points start getting coalescing, merging. What is the objective of clustering? Tightest and farthest. Farthest clusters are those which combine at a very high height. Nearest clusters are those which combine at a very low dendrogrammic scale. So those clusters which combine together at a very high dendrogrammic level, they are the farthest clusters. All of you okay? So in my dendrogram, I should be looking for clusters which combine at a very high level. These are farthest and tightest. What we do here is, visually looking at this, I decide at what dendrogrammic threshold should I draw a line. When I draw a horizontal line, that horizontal line will cut vertical lines. As many vertical lines it cuts, that many clusters you get. So if I draw a line at this point, I get 1, 2, 3 clusters. Of the 3 clusters, one of them is an outlier. It has only one data point. But these two looks like they're good clusters. If I draw a dendrogrammic horizontal line at 1, 2, 3.5 or something, then I get 1, 2, 3, 4 clusters. But then, I mean, these two clusters, I mean, they're coalescing just above 0.4, so it's not a good idea. Look at the next plot. Same data set is shown here as dendrogrammic. Okay. If I draw my threshold somewhere here, I'll get clusters and I'll not be able to distinguish. I'll not be able to understand what the clusters are saying. They'll be like box plots overlapping each other. If I shift towards higher values of dendrogrammic distance, then here, for example, 3, I'll get 3 clusters which are very far away from each other. Dendrogrammic distance between the clusters is very large, and they are all balanced clusters. So dendrogram tells you visually how many logical clusters are likely to be there. Logical clusters are those clusters which meet at a very high dendrogrammic distance. Looking at this visual stuff, I can go back and redo my k-means. So the purpose of hierarchical clustering is this. Now, which are the 2 points which are closest to each other here as per this? B and F, right? These are the closest points. So what hierarchical clustering algorithm will do is it will merge these two into one cluster first. So it will show you pictorially like this, where B and F are merging at a dendrogrammic distance of 0.2. 0, 1, 2. This 2 is this 2. So they get merged into one. At this level, B and F become one data point. Okay. So I get my new matrix, distance matrix. Now I need to find out the distance between BF and other data points. The distance between BF and other data points is nothing but B versus C, F versus C, which is the max. Why max? Because we've gone for max. So it does this for all the data points, and you get the distance between BF and all the data points listed out here. And rest of them remain the Euclidean distance which you borrowed from. Now in this matrix, which are the clusters which are closest? 0.25. This is the least. So now what the algorithm will do is it will merge these two clusters into one. So pictorially it will show you this, where A and E are merging at 0.25. Once again, it will recalculate the distance matrix, and this will continue to go on until all the data points have become part of a large supercluster, the mega cluster. This is the root node of your decision tree. This point is this. So when I look at my dendrograms, it gives me an idea about how many clusters are likely to be. I should be looking clusters I should come from the top, come down, and I should decide where I need to draw the horizontal line. Wherever you draw the horizontal line, make sure the clusters that you get are farthest from each other. If I draw a horizontal line here, I'll get 1, 2, 3, 4, 5, 6, 7 clusters. But those 7 clusters are same as your data points. If I draw a horizontal line here, I'll get 1, 2, 3, 4, 5 clusters. But no use. These 5 clusters are mostly your original data set itself. You won't be able to understand any logical groupings, nothing will come out of it. So we always look for clusters which merge at a very high level, and they are equally balanced, populated. It should not be that one is a large Jupiter, another one is a small moon. We don't want that clustering also. Yes.
So using this diagram, there should be 2 clusters.
2 or
because
3.
Because 3 is that D is outlier.
This is outlier, and this is outlier. So maybe I'll have 3 clusters or maybe 2 clusters. You're right. So I'll get meaningful information when I go for k is equal to 2 or 3. I need to check out which one. All right. So another way people draw is horizontally. And in this case, as probably it's coming out, there are 3 clusters here. We can see that there are 3 logical clusters. So I have to draw the line somewhere here. When I do this, one cluster is an outlier. Okay, one cluster is an outlier. There's only one data point in that cluster, but otherwise I'll get 3 good clusters. Very good interpretation of dendrograms. How do they use dendrograms in clustering? I've taken this picture from this URL. Okay, but a point of advice, a point of caution: the structure of your clusters will completely change depending on which method you use to combine clusters. If I use a different method, say single linkage, the structure of the tree will completely change. Generally, in data science, we go for centroid-based max or the average. Single linkage we avoid, because single linkage clusters can give you amoeba-shaped clusters in your mathematical space, no particular shape, and they become difficult to interpret. We want spherical clusters, and spherical clusters come out of this average and max distance. These two generally give you spherical clusters. When I say clusters, I mean clusters, superclusters, superclusters. Spherical. Then I have to go and see the data. I'll put these cluster IDs back into these records and go and see the attributes of these records. What is it that makes them come together in a cluster? Then I'll give them a label. I'll say, okay, these are a bunch of people who are interested in sports. These are a bunch of people who are interested in politics. So I will have to interpret those clusters and put a label on those clusters. That labeling is a manual effort, meaningful label. Algorithm will give you the labels in form of cluster ID 0, 1, 2, 3, but meaningless. The meaning part will come from our analysis. We have to do it.
But when you have multiple data points, more data points, right? That when you
So convert them into box plots and see, based on box plots you interpret. Based on box plots you interpret. What I'll do is I'll dig out that one example of tech support analysis and I'll tell you how we interpret the clusters using box plots. We'll do that. Yeah?
So we went through the tech support analysis.
We have gone through that? When?
Yeah.
No, during
the session.
This, session actually, we have gone.
Last week?
Last
then you would have.
We went through the box plots. We spent a lot of time on the box plot session.
Yeah. So I always use box plots to interpret the clusters. A lot of people make use of the centroids to interpret the clusters. You want to know how they do it? I'll just take a fictitious example. Now you imagine you have 2 dimensions. And in these 2 dimensions, this is interest in sports. This is interest in music. Politics is a dirty word. Music. Interest in music. Something of that. Okay. Now you find a cluster here and centroid here. You find a cluster here and centroid here. Okay. And you find a cluster here, centroid. Can you interpret these clusters for me? Can you interpret these 3 clusters? Correct. So these people are those bunch of people who are more interested in listening to music, playing music, but less interested in sports. They'll spend most of the time with guitars and all those things. Whereas these guys, you'll find most of them always on some football field or cricket field, probably watching sports. Okay, these guys do both. How did you interpret this? You interpreted this based on the position of the centroids on the various dimensions. Keep in mind, we have converted them to scale them into z-scores, which means this is 0th value in sports. This is 0. These are all negative. These are all positive. 0. These are all negative. These are all positive. These are a bunch of people who are positive on music but negative on sports. These are a bunch of people who are positive in sports as well as music. So these guys like sport and music. These guys like only sport, not music. You interpret the clusters based on their position of the centroids on the various dimensions. But this is not easy. When the number of dimensions is too many, it's not easy. In such cases, we make use of box plots to interpret the clusters. Box plots would give you the same thing. Move on, shall we? Okay.
Yes. That if you are changing this distance measure like completeness,
yes,
is it possible we will get the number of clusters also different?
Yeah, absolutely.
Then if we are using this number, that 3 clusters, and using k-means, then that also we are doing it wrong. Right?
Exactly. So finally you will come to know whether what you've done is right or wrong is when you are able to interpret the clusters meaningfully. So visually, when the box plots come very far away, separated from each other on those dimensions, then you can say, okay, I think I got good clusters. But if the box plots are overlapping in most of the dimensions, you are in trouble. So you might have to go back and change your distance calculation method both at the data point level as well as cluster level. Yes. Yes.
But then in those particular cases, is there any problem with the elbow method that it is not a
No. Both elbow method, this method, and the Celote analysis, because you said you have done Celote, all these 3 methods should converge to the same k value. All these 3 methods should converge to the same value. At least they should point out the range, the right range. One can't say k is 5, the other says k is 3, the next says k is 15. That should not happen. Visual way of telling you what are the structures in your data set. It all depends on what kind of cluster merging mechanisms you're using, single linkage, max linkage. The structures might change. Only thing is, these structures may not really exist. You have to be careful. If you go very low in your dendrogrammic distance, you're taking a risk such structures may not really exist. But when you're on the higher side of the dendrogrammic distance, very likely you're looking at logical clusters. Okay, finally, one very important point when you're going to do hierarchical clustering is what is called the cophonetic coefficient. And you already know the formula. It's just a wine in different bottle. Same old wine in different bottle. So we use a metric called cophonetic correlation coefficient. What it means is, when you build this tree to represent the distance between the data points at different levels, how much of the original distance between the data points was maintained in the dendrogrammic distance? What do you mean by that? Between these data points, there is some Euclidean distance, the original distance matrix. What is the correlation between that matrix and the final dendrogrammic matrix that you created? What is the correlation? There has to be a correlation. They should be linked to each other, correlated to each other. This original distance matrix based on Euclidean distance. This is the dendrogrammic distance I'm creating at every level, 2 level, 3 level, 4 level. How much of this original distance is reflected in this dendrogrammic distance? That ratio is called cophonetic correlation coefficient. It's nothing but same correlation formula, xi minus x bar into yi minus y bar divided by standard deviation of the two. It's the same correlation formula. I'll show you the formula. Don't get hassled with the formula. This is the formula. If I take all the original distance and find out the x bar is shown as x. If I take all the cophonetic distances and represent their bar, the average is t, xi minus x bar, yi minus y bar divided by standard deviations. Okay, let me show this to you on board. The distance between two data points, okay, this is the Euclidean distance. Now, this belongs to one cluster, this belongs to another cluster. And you're using this cluster joining mechanisms, the distance calculation mechanism, say you used a distance called centroid-based distance. Once this data point belongs to this cluster, it loses its identity. It is represented by the centroid. Once this data point has belonged to this cluster, it loses its identity. It is represented by this centroid. So now the distance between these 2 points, A and B, is Euclidean distance is this, but dendrogrammic distance is this. The dendrogrammic distance between A and B is this, assuming you take centroids as distance calculation method. If you use max linkage, the distance will be something else. If you use single linkage, the distance will be, suppose I use single linkage. So the dendrogrammic distance between A and B is now this. So whichever linkage method you use, how close that method is to the original distance calculation. Why do we say this? Why are we doing this? Simple. Now look at this. If you have tightest and farthest clusters, farthest clusters, you will see that their Euclidean distance between data points and the dendrogrammic distance between data points will be very close to each other. If the clusters are loose, then the Euclidean distance between the data points and the dendrogrammic distance data points will not converge. So you achieve the objective of tightest and farthest. Your Euclidean distance and your dendrogrammic distance, whichever methodology you use, will be very close to each other. They'll correlate. So when the coefficient of correlation is close to 1, that indicates that the dendrogram has preserved the original Euclidean distance. If the coefficient of correlation is very close to 0 or 0.5, oh, not good. That means you're having very loose clusters. So when you do hierarchical clustering, it will throw out this coefficient to you. Based on this coefficient, you can decide whether the linkage methods that you used for clusters is the right linkage method, or should I change and try something else. Okay. There's one more linkage method, which is, for some reason, I don't know why it's not shown. It's called WARD, W-A-R-D. what WARD does is, it looks at these clusters and finds out on combining which clusters, on combining which clusters will the resultant clusters have maximum variance, increase in variance. If I combine these two clusters, the variance increases phenomenally. If I combine these two clusters, the variance increases but not as much. Right? So what distance will combine those two clusters which result in minimal increase in variance in the supercluster? Minimal increase in variance in the supercluster. That is called WARD distance. But usually we use max linkage and average linkage.
Because we want spherical clusters.
Hey, no problem, that's okay.
We are doing this linkage and all on the cluster side.
Yeah.
First we have to form the clusters.
No, you tell what methodology you use to form the cluster, the algorithm will use that methodology to form the cluster.
So to calculate the distance between the red and yellow we said, so red is one cluster and the yellow is one cluster, or only the data?
That has been formed, the red and yellow has been formed in the previous iteration. In the next iteration, which cluster should I merge? So every iteration will be merging clusters. Which cluster should I merge? That depends on what method you have used for linking the clusters. So when you first start from the first iteration, in first iteration, all the data points are my clusters. So which cluster should I merge? Euclidean distance. So first iteration over. Second iteration, now I have clusters to merge. How do I merge? Then the linkage methods come into play.
As we see here, like D can come as an outlier.
D can come as an outlier? D can come as an outlier, okay.
And that can change our cluster, like we will take D as a cluster.
Oh, absolutely. In clustering, outliers will form their own cluster. Yeah, it can happen. D is the farthest here, so it can be an outlier. It can end up creating a separate cluster of its own. Can happen. Dimensions, the correlation happens at every iteration. Okay, it's basically xi minus x bar, yi minus y bar. So all these distances, this triangle, sum it up, divide by total number of data points, that is my x bar of this. So xi minus x bar, same way yi minus y bar here, all the dendrogrammic distance, total it up, divide by number of data points. So keep doing this at every iteration. So shall we do a hierarchical clustering on a wine data set? Yeah, this wine data set, I think we've already seen this. And the objective is basically to build a model where we can predict the class of the wine based on the attributes. But before we do that, make use of your exploratory data analytics clustering and see whether some useful information comes out of this data set, which can be used to find the direction in your supervised methods. Right? So that is the objective. So this is my data, the header data. I'm going to move on. And based on a pair analysis, pair plot analysis, once again, I'm using this to guess the number of clusters. In the first dimension, a single Gaussian with some bumps here and there. But in the second Gaussian, we can clearly see, in the second KDE, we can clearly see at least 2 Gaussians. Yeah. In the third one, 3. In the fourth one, there's one large and followed by small, not reliable. This can become a Jupiter and this can become moons, not good clustering. Same way here also, same way this also. In this, you see there are 2 clusters, one behind the other. In fact, 3 Gaussians sitting here. So based on this diagonal analysis of the KDE, look at this. At least 3 clusters, but looks like many small clusters. So you can drop this. Okay, you can drop this. This is the target variable which is causing the clustering. Since we're going to predict the quality, you can drop this. But what you're seeing on the other dimensions is somewhere 3 clusters. You're seeing some 3 clusters hidden in these dimensions. All of you okay? Move on. I'm making use of agglomerative clustering. I'm using a distance calculation method, Euclidean 6. Okay. I'm specifying number of clusters here. Don't get confused with this. Agglomerative clustering will print out the dendrogram to me. Based on the dendrogram, I'll decide how many clusters I need. But this algorithm requires you to input number of clusters. So let this be the first iteration where the number of clusters is some random number. Don't worry about this. The reason why the algorithm needs this is the output of this algorithm is going to be centroids. How many centroids to generate? So generate 6. We'll see it later whether 6 is optimal or not. Okay. So this 6 is a ballpark estimate, so may not be reliable, but it needs it, so we're given it. You fit the data to it. This is where the clusters will be formed, the hierarchy will be formed. Okay. Oh, I've not run this code. Okay, no problem. Let me move down. And there you go. I asked for 6 clusters, so it's given me 6 labels. And it has given me the centroids of the 6 labels. This is not important. I come down, straight down. Okay. What I'm doing here is, since this methodology stores these labels back into the data frame itself, I'm grouping the data by labels. All the records which belong to cluster 0 should come together, cluster 1 should come together, so on and so forth. This is exactly what we did for box plot in the k-means clustering. It's the same stuff. I'll use this later on. So come straight down from SciPy, Scientific Python, clustering libraries, hierarchical clustering. I'm making use of cophonetic distance calculation, coefficient calculation, dendrograms, and the linkage methods. Now look at this. I'm going to use on this wine dataset average linkage method. Okay, and that average linkage method, I'm going to feed it to this cophonetic coefficient calculator. This calculator is giving me a cophonetic coefficient of 83%, which means 83% of the original distance between data points has been maintained by this dendrogram. Which dendrogram? We'll see it down the line. When I plot the dendrogram, this is the dendrogram I'll get. Okay. In this dendrogram, these are all the record levels. You see a smudge here. This is because there are too many records. It can't be shown on the screen. Okay, and these are all individual records which are getting clubbed at different dendrogrammic distance. Not very good place to be in. What we would like to be in is, we would like to be in a place which is very high in dendrogrammic distance. So in this, if you look at this command, this plot, I've given a threshold here. What I've said here is, at the threshold of 40, draw a horizontal line. So at the threshold of 40, which is somewhere here below 50, when you draw a horizontal line, it cuts 1, 2, 3, and 4 vertical lines, and you get 4 different clusters: red, light blue, green, and this one. If I change this threshold, I think let me run this and show it to you. Let's not jump these things. Give me 1 second, please. I'll just run this properly. We've done this. Yeah. Okay. This is the one we had originally. Okay. If I change this linkage method from 40 to say 80 and redraw this, it's a very computationally intensive algorithm, k-means and hierarchical. So many distance calculations have to happen. Yeah. Now look at this. At a dendrogrammic distance of 80, which means you are somewhere here. When you draw a horizontal line, you're going to cut only one vertical axis. That means all data points become one cluster, super cluster. If I change this to say around, say I want 2 clusters, I make it 60. It'll recalculate all those things. There you go. I got 2 clusters. But as you can see, one cluster is a very large cluster, the other is very small clusters. If I go for 2 small clusters in the red cluster, if I do that, then I'll have to give a very low threshold. But when you give low threshold, your clusters become uninterpretable because there's not much difference between the clusters. So that is the dilemma. Maybe the linkage method I've used is not right. So the linkage method which I used, if I change the linkage method, say now in this case I'm changing the linkage method here, I'm changing the linkage method to where is complete. Earlier it was average. Now I change it to complete means max linkage. When I redo this analysis, I get different clusters. So every time you change the distance of finding the nearest clusters, distance methodology finding nearest, your decision trees will change. Once again, look at this. The reason why I'm not happy with this is, if I want equally balanced clusters, I'll have to give a very low threshold. If I give a very low threshold, it becomes meaningless clusters. But at a very high threshold, I'm getting imbalanced clusters. One very large cluster, one very small cluster. Not a good idea. So I change the distance calculation method again. This time I take WARD. I draw the dendrograms, and WARD seems to give slightly better results. Now I'm getting at least, if I drew a threshold at say 450 or something, I'm likely to get 1, 2, 3, and 4 clusters, and the clusters are equally balanced, more or less of similar size. Are you able to see that? So if I draw my threshold at this point, somewhere at this point, if I draw a horizontal line, I get 1 cluster, 2 clusters, 3 clusters, 4 clusters, and the cluster size are similar, almost similar cluster size. Let's look at the cophonetic coefficient. The cophonetic coefficient for WARD is only 66%. Only 66% of the original distance has been maintained by your dendrogrammic distance. Many times, this 66% is actually good. We consider it as a good coefficient. You will never find yourself in a situation where the cophonetic correlation coefficient is 1. It will never happen. Crossing the threshold of 70 itself is difficult. So we have to take a call whether this is reliable and look at the dendrogram. At what threshold I get meaningful clusters? Is that threshold sufficient for me to separate or think that the clusters are different from each other? So what I would do in this case is, I'll go ahead and do a k-means clustering based on this. Whether this is good or not will be decided by whether I'm able to interpret the clusters or not. So finally, the quality of the clusters is subjective. Okay, so these are tools at your disposal for you to decide whether clusters are good clusters or not, but the quality of the clusters will be subjective. Are you able to interpret the clusters meaningfully? And that's a manual process, unfortunately. No, I can use the same centroid, same groupation from this also, I can do that. But I always make use of this to also do k-means, and this, are they giving me similar results? The clusters I get in k-means, the 4 clusters I get in k-means, and the 4 clusters I get here, if I go back and rerun this with 4 clusters, these 4 clusters are giving me similar results. That's what I'll find.
But the cluster group can be different through this.
If they are different, very different, then it's not reliable.
But it can be different.
They will be different.
It will be different.
Guaranteed to be different. How much is the degree of difference? In one cluster it says this is a sedan car, in the other cluster I'm not able to interpret it. Sorry. Clusters will be different. Even though you get 4 clusters both in hierarchy and both in k-means, you get 4. They will be different, but difference should not be too much.
You run both of them independently and compare them.
See, the reason why we do so much of things in clustering is this is going to lay the foundation for your supervised methods. You form your alternate hypothesis based on this.
But what is the point in comparing if the clusters are going to be different from that methodology?
If there are 2 different uninterpretable, this guy is saying something, that guy is saying something, is useless. Then clustering mechanism itself is not reliable. If I'm able to see that the 2 clusters are giving similar interpretations, then I'm in a safe zone. Then I'll formulate my alternate hypothesis. I'll say for large cars, MPG cannot be predicted using my acceleration.
It again leads to the data handling.
Yes. All the magic happens in the data. That was my first sentence when I started this first engagement with you. Okay, this Silhouette analysis code, yeah. This code I have taken from scikit-learn user guide. Plotting the Silhouette analysis, it requires a lot of code just for plotting. Okay, so what I've done is, to explain the concept to you, I've taken this code from scikit-learn user guide. So this is my mathematical space or feature space. In this feature space, you are seeing four logical clusters, 4 natural clusters. Okay, but imagine we don't know how many clusters are there. We asked for 2. So it gave us 2 clusters. The algorithm, the k-means algorithm, has given you 2 clusters. In these 2 clusters, are these good clusters or not? We can find that out using what is called the Silhouette coefficients or Silhouette plots. What the Silhouette coefficient is, it's a ratio. Ratio of, take any data point, Take, for example, the green data point here, the green one. What is the average distance of this green point from all the points in its own cluster? The pairwise distance. Okay, what is the average distance of the green data point from all the data points in the same cluster? Versus, what is the average distance of this same green data point from the data points in other cluster? Okay, so we find out the ratio of this divided max of this distance or this distance. If the clusters are very tight and far away, I'll write down the formula here, Silhouette coefficient formula. The formula is max of, I'll take A comma B, where A represents the average distance of a data point from other points in the same cluster, the cluster to which it belongs. Okay, B is the distance of the data point from nearest data point in other cluster. Okay, so you take this one cluster, take any point here, find out the average distance of the point from the other points in the same cluster. Let's call it A. Find out the distance of this data point from the data point in the nearest cluster. So A by max of A comma B. Max of A comma B, if you have tightest and farthest clusters, it will always be B. The ratio will always be A by B. This will always max. Okay. Now, what you see here as a continuous plot is actually not a continuous plot. It is different lines placed on top of each other. Look at this edge. It is jagged. So these are lines placed on top of each other, each line for one particular green point. The Silhouette coefficient is max for the point which is farthest from the other cluster. The Silhouette coefficient, this one, the last row here, this is the Silhouette coefficient of the green point which is the closest to the other cluster. So here for this green point, the average distance of this point from the other points versus the distance of the other points in the other cluster, these two are almost similar. The ratio is almost coming to 1. Yeah. So this row, this green line over here is the Silhouette coefficient of the nearest point. This is the Silhouette coefficient of the farthest green point. Same way in black, In black, the farthest black point will have the highest syllotic coefficient. The nearest black point to the other cluster will have the least syllotic coefficient. And in between will be the other data points. Now, when you find this kind of a syllotic plot, where one cluster is very large, the other is small, you are in not a right zone. You are not in a right zone. Other thing is, you look at this red dashed lines. This red dashed line is average syllotic coefficient of all the points. Average syllotic coefficient of all the points is what this red line is. And as you can see, most of the black points have a syllotic coefficient less than the average. Not a good idea. When I change this from 2 to say 3 clusters, though there are 4 clusters, I don't know there are 4, so I try k is equal to 3. Once again you see the syllotic coefficients for each point in each cluster is shown here, and the black cluster is performing very poorly. Not a good idea. When I make this k is equal to 4, where it reflects the natural number of clusters you have in your data set, you will see that all the clusters cross the average syllotic coefficient boundary. And good part of the cluster is on the right side of the average syllotic coefficient. And their distributions are also similar in size. You got the tightest and natural clusters when you have right k. So syllotic coefficient is the ratio. The ratio on the numerator, you have the average distance of a point from its own clusters versus distance of the point from the nearest cluster. This ratio is called syllotic coefficient. When the clusters are touching each other, very close to each other, you will see that they are very close to the boundary. The black cluster is touching the other clusters. It's very close to the boundary. Yellow cluster is touching the other clusters. It's very close to the boundary. Whereas blue cluster is tight and far. Most of the data points have very good syllotic coefficients.
Looking at this diagram, how much is good in terms of the distance after the dotted line, right? Difficult to say that.
Overall, what it's telling you is all the clusters are crossing the points. Good. They are similar in size. Good. Okay. Of course, yellow cluster and the green cluster is still a concern, but that is because they're touching each other. They're touching each other. That's why you're finding that.
And again, to clarify on B, point B, is the distance of that data point versus every point in the nearest
cluster.
Nearest
cluster, yeah.
Average distance.
Yes, average distance. Yeah.
So the red.
I'll take her first, then I'll continue. Yeah.
So when we did this assignment, so we got one table, one matrix kind of thing, where the variance was there, average syllotic was there, and centroid was there, if I remember correctly. So if I have numbers, I mean, I think that this range between 0 to 1, and then for 2 cluster it was giving some average syllotic, then for 3 cluster it was giving some average syllotic number. So how to interpret that?
The max syllotic coefficient you get, the better the clustering is.
Okay, so for different 0 to 3, where I will get the max one, that I will...
That is the best syllotic coefficient. That is the best clustering.
And that I can consider
yes.
for further analysis.
Yes.
Okay. Got it. So variance should be minimum and this should be maximum.
Yeah, correct. So syllotic coefficient, elbow method, then visual analysis, all these methods should converge to a small range within which you should find your right clusters.
This brings us to the end of this tutorial on top data science projects. So thank you very much and have a great learning ahead. I want to introduce you to Great Learning Academy, a free learning initiative by Great Learning, where you can access over 200 plus courses with 1000 plus hours of free content on trending high-demand domains such as data science, machine learning, artificial intelligence, programming, cloud computing, digital marketing, DevOps, management, and many more absolutely free. Award-winning academicians and leading industry experts design these courses. You can also get a free certificate of completion when you enroll and complete these free courses. You also get access to the presentations, code, notebooks, datasets, and quiz. We have courses in English and Hindi to give you the best learning experience in the language you're comfortable with. Check out the description of this video to access the relevant course on Great Learning Academy. So what are you waiting for? Register now and start your learning journey today. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.